Thank you for that introduction. I'm not a chemist. I'm a physical chemist, by the way, which is a mixture of chemistry and physics, so I'm just straightening him out. But anyway, it's really a pleasure to be here. I really appreciate the opportunity to talk to you a little bit at pretty high level. I'm not going to go into super deep dives on any particular topic, but feel free to ask questions. And I think looking at the schedule, there's a lot of deep dives on many of the aspects I'll touch on today. But I mainly want to just give you a perspective on how we look at computational material science from the application side, people that are trying to solve problems that exist within technology or fundamental science using computers. Also, I'll go a little bit into, well, what happens if our methods that we have currently or our computational systems that we have currently can't solve that problem? What do we do then? And that will dive in a little bit of how we develop different types of approaches to solve problems that pop up during scientific exploration. Because typically when you do science, you never know what the result will be. Otherwise, it'd be kind of boring. So a lot of times what you think is going to happen doesn't happen, and then you spend all your time trying to figure out why it didn't happen, and you discover something that's pretty cool and more exciting in the end. So I'll go through things in sort of that perspective. So I just want to let you know it's pretty high level, not a lot of mathematical details, but believe me, there's plenty of them in there, and I think a lot of the talks will go into those details. Feel free to interrupt anytime. You can laugh or don't laugh at my jokes. There's a few in here, and I will probably just make up some as I go, like Vincent does. Very briefly, start off telling you a little bit of why anybody should care about material science in the first place. I think that probably everybody in here does. There's both physics, chemistry, and biology involved in this. Go into a little bit of a perspective in terms of nanoscience, what happens when you start making materials at the nanometer scale, what happens to the properties, what happens to the structures. Dive in some details on how we model these materials, both from a classical perspective, classical mechanics as a theory, and a quantum mechanics perspective, quantum mechanics being the theory. Few vignettes on how you can use those to solve problems that matter to the society, both in technology and fundamental science, and then drop into some new stuff. So the first part's mainly using first principle methods that are based upon actual theoretical foundations like classical mechanics and quantum mechanics. And the last part is based upon more statistical analysis, data analytics, artificial intelligence methods. I call those no principles. There's no theoretical construction of those. Those are just taking data and make correlations. Incredibly powerful what you can do with these things. So I wanted to go over that in the second part, and maybe this afternoon, and give you some examples of how that can be coupled with the first principles to solve some really, really hard problems that are actually meaningful to new materials and new technologies. Then I'll finish with a global story. So what the heck is a global story? Well, you have to wait till the last minute of 3 hours to hear that. Actually, I thought this was 4 hours, so, we'll see how it goes. So materials, why do we care? Well, if you look around you, anywhere, just look anywhere, everything that has any technological value to it is based upon materials. All of our advanced technologies are fundamentally based upon materials. And the advances that we have made in technologies are all due to the advances in materials. That range from the structural materials that we use in our buildings, to our roads, to our airplanes, to our cars, to the functional materials that we use in fancy LED lasers, to your cell phones, to optical electronic devices, to computers. Everywhere you look, all those advances we made is based upon advances in materials fundamentally themselves. So pretty important. So leadership in materials is fundamentally essential to leadership in technology. And we do want to be leaders in technology. And that is something the world desires. Madonna recognized this back last century. Most of you people probably weren't even alive then, when she sung this song that we live in a materials world and we are materials people. So, she knew this a long time ago. And then Lady Gaga said, well, ra, ra, ro, ra, ma, ma, gaga, oh, la, la, in this century. So, the music industry understands the importance of materials. Actually, if you look at that, you say, wow, it's a lot of elements. That must be a really novel, high entropy, solid solution. So industry cares, entertainment cares, everything depends upon materials. So you did laugh at one of my jokes, okay? So back at the early part of this century, actually it started last century, but it was kicked off around 2000 by Clinton. People realized that, if you take a big piece of material and you look at its properties and you scale that down, the properties start changing as a function of the size. And if you could control how you scale that down so that you put every atom where you want, you could really have potential to tweak out new properties that wouldn't be possible any other way. So back then we decided, what could you do if you could control materials all the way down to single electron coherence? Well, if you could control the coherence of the spin of an electron, you could start talking about quantum computing, quantum technology, sensing, telecommunications through quantum. If you could do controlled single electron, you have single electron transistors. You could talk about other things such as didactic programmed material, where you make a material that is programmed to form a particular shape and a particular function. Talk about active materials, materials that change over time as a function of the energies that provide them. You could imagine so many cool things, but you just need to be able to control those materials down to this nanometer scale. And ultimately, you need to control them down to a single atom level. Of course, Richard Feynman knew this a long time ago, right? Back in the 1950s, said, what could we do if we control, genius, right? Well, I'm going to tell you now, we can do it. So this is pretty exciting, right? And I'll show you toward the end of the talk this afternoon how we can do it and how we can actually put atoms where we need them, control them specifically to position them in a part of the material to give you spin coherence. So it's pretty exciting. I'll actually show this picture from when I was born of the nanoscience frontier. That's not when I was born, by the way, but it is a truly exciting frontier, and a lot of things that come out require developing new methods, because most of our methods are not developed to take into account some of the things that happen at this scale where electron correlation really, really is important. So we have to do some developments, but I'll go through some of these advances and show you an example right quick of why we are pretty excited about it. So a couple of years ago, we thought, well, what can we do that's scalable? Well, if you're moving a single atom around, you have a single atom, right? You need a lot of atoms or a lot of these single atom things to make a actual dent in technology, because it has to scale, right? You need millions of these. If you look at the semiconductor industry, these foundries make chips thousands and thousands a day. They don't make one. So it has to be scalable to be impactful to technology. So we were trying to figure out, how could we nanostructure a surface of a substrate that would not depend on being able to do it at a very small length scale. So I would like to be able to nanostructure this entire room, for example. So that's scaling, right? But you're scaling structures that are a nanometer size over this. So that's a lot of structures, right? A nanometer over 10 meters is a huge number of structures. So how do you do that? So what we've discovered is, if you construct a plasma-enhanced chemical vapor deposition chamber correctly, you can actually basically spray coat a surface of a silicon substrate at any length scale you want. You say, okay, so that's sort of like printing the back end of a TV screen, right? But what happens in this very high temperature extreme plasma condition is that if you look at the structures on that surface, basically it's all little spikes of something, okay? The precursors in this plasma-enhanced chamber, this is a very high temperature chamber that's based on plasma, are just ethane and ammonia. So we know that this material is carbon and some nitrogen. The percent of nitrogen that gets in this material is about 5%. If you zoom in on one of these little horns or these spikes, the diameter is about a nanometer. So the radius is about half a nanometer, 5 angstrom. Very, very sharp stuff. So it's basically a big cactus spiky material coating the entire surface. It's fairly uniformly coating the surface. Then we thought, well, what would happen if we applied electric field across that? Let's just make it an electrode. If you think about Gauss law, the size of a structure depends, electric field depends on the radius of the size of the structure, and we're talking the square, reciprocal of the square of the radius. So if you pass the current through this, there would be this enormous electric field at the aperture. And of course, the smaller that aperture or the apex of that structure, the higher the electric field. So we said, well, what happens in electric fields when you put molecules in a really extreme electric fields? We're talking 10 to 12 volts per centimeter type electric fields here, really huge. Well, you can blow them apart, right? In principle. Or you can weaken their chemical bonds. So we put this material on the silica structure into a electrochemical cell and passed into the electrochemical cell nitrogen gas. Okay. When the nitrogen molecule comes close to, basically always going to come close to one of these spikes because the whole surface is spikes, it weakens that nitrogen-nitrogen bond. So basically you're able to reduce the nitrogen molecule, which is a triple bond. It's really hard to break that bond, by the way, by this electric field driving it in a catalytic fashion. So this is a carbon-based material that can catalytically reduce about any molecular species that we've ever looked at. That's a pretty big deal. And the way it's a big deal is because it's at room temperature and room pressure. So if you think, how do we make ammonia right now? It's a Haber-Bosch process. Well, it's not room temperature, room pressure at all. It takes about 3% of all the world's energy to do that process. And we need ammonia for our food. It's fertilizer. So this is a non-transition metal-based catalytic process realized by nanostructuring carbon materials to be very spiky, having very sharp points, and using that to the advantage based upon the electric field. So that's pretty neat. We've also reduced carbon dioxide, this is a little bit more tricky, to ethanol directly. That's typically not possible. You usually go through a single carbon process. You usually go to methanol instead of ethanol. Ethanol is good, right? We liked it sometimes when we eat as a beverage, and it's also not a bad fuel, it turns out. Most of us like it for beer. But funny story, another funny story hopefully, is that this is technologically interesting to industry, right? Because it's a very energy efficient way of making different upcycling of basically waste gases like nitrogen and carbon dioxide. So a bunch of wineries and breweries approached us and licensed this technology. So you think about a brewery, it's a fermentation process. Fermentation generates a huge amount of carbon dioxide, which increases their carbon footprint, and they get penalized for that. Now they can take the CO2 directly and convert it back into, well, ethanol, their product. So it doubles the value of their actual product. So we hope they'll call this nano beer, and then they can sell it for $50 a bottle, right? But it is licensed. There is companies using this technology already. But I just wanted to give you an example. We say all these things, but this actually does happen, and it actually does matter how things are structured, and it can be really impactful to society and industry. So next time you get a beer, it says nano beer, you'll know where it came from. So, things sometimes don't always do what we think. Please read this because it's not funny unless you don't read it. Sometimes we observe stuff and think, gee, that shouldn't work that way. That's not what my physical chemistry or my physics or biology said. What the heck's going on? So it's that I'm from Tennessee, so I say all the time. That's the element of uncertainty. So that's where actual digging into the details and studying the fundamentals of physics and chemistry that's driving the phenomena becomes important. And that's where theoretical models and simulation play the biggest role, is understanding what's going on, and then from the understanding, predicting new things that could happen if you did something differently. So, a lot of words here, basically just saying that we can study materials, both chemical materials or solid state materials, by solving a few equations. There's not that many. They're kind of complicated equations. One is the Schrodinger equation. It's just a linear partial difference equation. It's not that bad, except it's got a lot of things in it. And there's various forms of classical equations, Newton's equations, Maxwell's equations, some of the hydrodynamics equations. These are all classical. So we basically put these equations on a computer and we solve them. And that's how we do computational science. If you do this correctly, caveat correctly is important, you can start understanding what's going on. Like I explained the carbon nanospike, I mean, that wasn't just, we just said, aha, we know what's going on. We actually did the calculation to find electric fields and did the calculation to see the actual reduction process on the computer. So if you can solve these equations for the right models, you can really dig out a lot of understanding and start predicting new things, like what would happen if I changed the temperature or pressure, or what if I put a different electric field. You can scope out a lot of parameters, a lot of different environmental conditions that would take a lot of time doing experimentally, maybe not even conceivable experimentally. So this is a very, very powerful technique. Materials, there's lots of them. I won't harp on any particular material. I just want to let you see the breadth of the different types of materials that these equations are pertinent to. The more recent hyped up area is called quantum materials. There's a reason why it's hyped up. It's actually a realistic expectation that these materials can enable quantum type information sciences, such as telecommunications or sensors or even quantum computers. But many other aspects are very complicated because the electrons really know about the electrons. They're strongly correlated. DFT doesn't work. There's a lot of real issues there that make it complicated. Structural materials, alloys, superalloys, the Lady Gaga's material, the high entropy alloy. Very important class of materials for almost all of our infrastructure. Polymers, soft matter materials, responsive, self-healing materials, the stuff that gets in the ocean and never goes away. Materials, we need to be able to make them go away. All right. To do that, you got to understand how to do that. So, a lot of exciting stuff in that area. Interfacial chemistry, such as in the energy storage and energy conversion, batteries, supercapacitors, solar cells, nuclear materials. Very extreme conditions, bombarded by ionizing and radiation constantly, extreme temperatures. So it's a whole lot of different materials, and those equations are pertinent to all of this. So you can see the power behind these simple differential equations if we can solve them and set up the correct models. You can study this diverse class of materials, and you can make an impact to the next generation of nuclear reactors, for example, or the next generation of batteries, or the next generation of quantum materials for quantum computing or information sciences. So it's pretty exciting, I think, honestly. I think, very different than when I was your age. Which the computer I had was about 10,000 times less powerful than my cell phone, right? It was a kilobyte type system. So I never would have dreamed this would have been possible when I was your age, but it's possible now. So I think it's pretty exciting times. So how do we go about doing these simulations? This is diverse materials and solving those equations. So one way to look at it is we have a big toolkit. The toolkit can use classical mechanics or quantum mechanics or even continuum type mechanics. And these different tools are appropriate for different lengths and time scales. If you're looking at quantum, you're solving Schrödinger's equations, a many-body problem, and you're looking at electrons. So it scales as the number of electrons, not the number of atoms. So you're going to do smaller systems, and you're looking at angstrom scale to maybe nanometers, and you're looking at picoseconds to maybe nanoseconds. If you use an all-atom system, you can also look at angstroms. Every atom is treated as an atom, and I'll go through all this in more detail. I just want to show you the different length and time scales. You can look at different time scales, coarse graining the atoms to units or structural units. You can look at different length and time scales. And then you can look at the very long lengths and time scales, modeling the entire table or modeling the entire bridge structure. So we have all these tools. All these tools are developed to some extent, but there's a lot missing still. So I think there's a lot to be excited about if you're in the area of developing these tools. Before I go too much further, again, we look at this sort of like a computational or virtual microscope. We're peeking into what's going on with the fundamental physics at the electron and atom scale inside of any type of material. It's material agnostic to a great extent. So it's a powerful, powerful tool, and it's complementary to most experimental techniques. And I'll show you some of that as I walk through. So a few concepts. I don't know anybody here, so I don't know how deep of basis you have in computational modeling. So sometimes words are thrown out, and I have already thrown out a bunch of them, so hopefully I'll clarify some of them as I go through this. Some of the things you'll hear is models. What was the model you used? And I'll go through what that really means. Sometimes you'll hear things like coordinate systems, Cartesian spherical coordinates, and these are important. It changes the set of differential equations you have. You'll hear people talk about potential energy surface, potential energy functions, or force fields. I like force fields a lot. Sounds like Star Wars. But they're basically the same thing. When I grew up, there was no Star Wars. And you say, wow, holy crap, you are as old as that big old frontier thing, aren't you? But it wasn't, actually. So we called it potential energy. But now we call it force fields. Theory, I already went through the theories. Basically, the main theories that we're going to be talking about are classical mechanics and quantum mechanics. That's a pretty good set of theories. Basically Newton's equations and Schrodinger's equations. So it's Newton's second law. And simulation, I already showed you the different types of simulation techniques, ranging from quantum simulations at the electron level to atomistic to coarse-grained continuum. Sometimes we put them together and they're hybrids. They treat different scales at the same time. Integrators, how do you solve those equations? Solving the differential equation, you've got to integrate those equations to solve them, and you integrate them over time. So I'll go through that and tell you how that's done. So modeling and simulation, what's the difference, right? I mean, sometimes you think there's no difference. Well, modeling just refers to some mathematical representation of what you really have. It's not exact, right? It's just a model. It's like a map, right? It's not to scale. It's not got every bend and curve in it. That's a good analogy to subway systems. It's very representative and you can get around, but it doesn't have everything. Simulation is just solving the equations that result from the model. That's it. Okay, so that's sort of the basis of some of the terminology. And now I'm going to go in and start talking about some of the fundamental equations and how we solve them, and show you how that is meaningful and how we used it to solve an existing problem. So starting with all atom, these are treating everything in the material as little ball. We need to know what the little balls are, which atoms are in the material, and how they sort of are hooked together. If we do know that, then we can use the Newton's second law, which is force equals mass times acceleration. Ends up having second order differential equations that define, if you solve that, you can find all the positions of all the atoms in that, or all the particles in that material as a function of time. So you get a trajectory of where the atoms are going and what they're doing at any given time if you can solve that. You need that potential. The first derivative of the potential gives you the force. And so basically to set up a computer code, you need to write down the potential and then take the derivatives. And then you have your differential equations, and then you need to solve them. And that's it. That's simple, really. You say, well, nobody seems to be surprised. Okay. Well, materials are diverse, and if you look at it from a chemistry or even a physics perspective, or even biology, we know that things are sort of like to bond in certain ways. Some of them bond in ionic bonds, some bond in covalent bonds, and I do believe they actually are covalent bonds. Some are more metallic oxides, and they also have some have funky behavior because of electron correlation. But we need to be able to write down models for these things. The easiest thing to do to start with is think of it as in the molecular sense, and this is a chemist coming out. A ball spring model. Everybody sees these. These are pretty pictures. This is actually a benzene molecule, for example. In order to have a ball spring model, you sort of need to know what every atom is in that material. Is it hydrogen, carbon, nitrogen, lead? You need to know the atom type, and you need to sort of know where they are. a good guess of where they set. Most typically, we will know that. You can know that from spectroscopy, you can know that from crystallography, or you can just make it up. Try not to do the latter. Making it up sometimes is a disaster. But if you know all the atoms and you put them where they should be, things will be good. Now, if you put a wrong atom where, if you make that carbon a lead, well, it's not going to work out well for you, right? So we do need to know the atom types, and you can learn that from many different experimental techniques. Once you know the atom types and their connectivities, we can write down the potential energy function, and we can just separate it out and say, well, anything that's close to each other that's bonded will be a 2-body term, and then if there's 3 bodies, we'll call it a 3-body term. That can be defined by an angle. That's a bend angle. This can be a stretch. You have 4 atoms connected together, you're going to have a torsional angle or dihedral angle. And then if they're not bonded directly together, you have short-range interactions like van der Waals interactions, hydrogen bonds, and long-range interactions. These are charge interactions. Charge scales is 1 over R. It goes on forever, whereas the van der Waals is more like 1 over R6. So we can write down pretty much any type of molecule in this simple fashion by just defining the 2, 3, 4-body short-range and long-range terms. And these are sort of ideal potential energy functions that people use. There's many, many more. So once you write that down, you have your energy, you take the derivative of that, get your forces, solve Newton's equation by integrate it, you have a molecular dynamics simulation. So that is the model, and that model can be used to define almost any material. Simple, right? Okay. What kind of functions are out there? Well, there's a lot. That's where it gets confusing, all right? How do I choose the right potential energy function? The best way to do it is not use classical mechanics at all, but I'm talking about classical mechanics now, so I'm going to use classical mechanics. So, any non-bonding interaction you can define with a Lennard-Jones function. Lennard-Jones is a very simple potential energy function, and you can look it up. I'm not going to show you what it is, but if you plot it, it looks pretty much like that. It's very short-range interactions. You can define all the particles in a system like a gas this way. You can just set it up. Super simple to set that calculation up. Super fast calculation. Do billions of atoms that way. You can look at gas expansion as a function of temperature. You can derive PV equals nRT, really complicated things like that. Ideal gas laws. It all comes out of that. And you can do it all just with the simple potential. Now, if you want to look at molecules or solutions of materials and of different molecules, you have to go to something a little bit more complicated. There's many-body potentials, which take in the 2, 3, 4-body bonded terms and the non-bonded terms. There's a whole slew of these. They all work. That's the scary part, is they always will do something. And that's where it gets a little tedious and dangerous, is you're always going to get a result, okay? I'll go over how you have to be careful with that in a bit. There's reactive potentials. If you want to look at chemistry, bonds break, and sometimes they are made during different temperatures or different electric fields or different environments. If you have a harmonic oscillator, the bond can't break. You can pull forever, the energy just will go to infinity. So you have to have reactive potentials if you want to do anything that has any chemistry in it or charge transfer. There's a whole bunch of those. As I mentioned, one of the better ways is just don't assume any classical potential at all or analytical potential. Use quantum mechanics, and quantum mechanics will find the energy associated with its neighbor. The only problem with that is you can't do very many atoms if you do that. So if you want to do a very large-scale system, or you want to model a material or a thin film, you're going to have trouble with the quantum mechanics. You're going to have, if there's no periodicity, you're going to have to settle for some of these lower-level classical models. The classical model can be really, really good. You just have to apply it where it's the answers you're trying to get are addressable. One other class that is kind of pseudo-quantum mechanics is called type binding. It's a very strongly used technique within physics. It's basically gives you the electronic structure for about 1/1000th of the cost of the quantum approaches. So they can do a lot larger systems, and it's using quantum mechanics, so it actually is going to allow you to do chemistry and study all the things that one might want to do if you're looking at materials that actually do undergo chemical reactions. So that's the sort of range, and I won't write down the functions of any of these, but I list one down here and the Leonard Jones up here as two examples. You can easily look them up. In most books on simulation will have some of the details on these techniques, but if you want to hear more, I'm glad to jump into that. Okay. So if you have the potential, you can do lots of stuff, right? You can follow the equations of motion over time by integrating them, or you can just set the first derivative to 0 and find the minimum. That's called molecular mechanics, believe it or not. Very simple. Of course, you have thousands of atoms, and you have to optimize thousands of atoms. So conjugate gradient, steepest descent. This is basically steepest descent. If you set the derivative, first derivative to 0 and solve for the positions, you'll find the minimum in a very complicated potential energy surface. Sometimes you get stuck in a metastable state, and there's methods to allow you to get out of it. So biologists uses this a lot, right? So they have these horrifying proteins and enzymes that are monstrous, and they fold all over the place, and they fold differently in different environments, different solvents. And so they don't always care about the dynamics, they just want to know the structure. And so this is super fast, can do millions of atoms and very complicated potential energy surfaces. Again, you're not solving any differential equation here, you're just solving for the first derivative being equal to 0. Also very easy to implement and very easy to solve. You can even use a Newton method. You can do it probably while you're sitting there right now. Pretty quick. The other good thing is you don't actually have to write the algorithm to solve these things. They exist. You just get the library and you just plug it in. So it's pretty cool. Now, if you want to watch the dynamics, the time dependence of the particles that occur at different temperatures and pressure, you need to do actually solve the differential equations as defined by Newton's second law. Not that bad, just quite a few of them, and there's more if you have more particles. So if you're doing billions, you've got lots of them. And if you want to look at them evolving over time for long periods of time, simulation time, not real time, it becomes a computational challenge, right? If you have 10 million second order differential equations and you have to solve it 200 trillion times in order to look at 2 nanoseconds of time evolution, that's pretty hard. It's not hard, it's a lot of calculation, right? So you won't do that on your desktop, for example. But I'll get to how you can do that. So we do want to follow lots of atoms, and we want to follow them over time. We want to do stuff to them. We want to change the temperature. We want to change the pressure. We want to apply electric field. We want to put them in a solvent. We want to change the solvent. We want to see what happens. We don't want to have to go in the lab and get our hands dirty. We want to do it on a computer. And you can do this. And it is a many-body problem. It's much simpler, as I mentioned, than quantum mechanics, but it is something that has great value because it can do larger systems, and you can tease out some pretty cool information. Basically, to get started, this is a fundamental algorithm. This is all it is. You have to know where your particles are, what they are. You put them in some position, you give them some velocities. You can do that with the Boltzmann distribution of energy. It's pretty simple. You calculate the force, which is the first derivative of you do that on the computer, and then you move the particles with a time step that is going to solve that differential equation, so you know the positions and how they changed after that time step. And you do that, and you do that till you're tired, and you get a lot of results, all the positions, all the velocities over the time at that condition, for that boundary condition. And you look at it on the computer, you analyze it, you compute correlation functions, and you can use those correlations, compare directly to experiment. You get spectroscopy data directly from this. A lot of information just by following the positions and velocities of all the atoms in the material. And that's the simple algorithm. If you would like to see it in the code, you can just take a peek in, Adam Tisley or Franklin Smith have some really nice subroutines that you can just grab right directly out of the book. And pretty good books. So I would recommend those if you have spare time and are interested in reading more details on the implementation on the computer. Integrators, there's a bunch of them. You don't have to get fancy, just a simple Verlet central difference approach, which is pretty simple. The position at time t plus a time step that you're using for your integrator is just equal to this. You can solve that at any delta t. Be careful with the delta t. That's the integrator time step. If it's too big, you'll jump across too big of a, your integrator is too, well, the differential equation is too stiff and you'll get a really bad result, right? It'll explode. Your differential equation will explode. So you don't want to just throw in any delta t. The delta t needs to be determined on the frequencies or time dependencies of the material. Most materials you're going to be looking at femtoseconds and maybe hundreds of femtoseconds for this delta t. So if you're wanting to study a material's dynamics and time dependence over, say, an hour, and you're taking steps one at a time, by the way, at 10 to the minus 15 seconds, you can imagine how long that'll take, right? So, but that's the way it is. Verlet is a fine integrator. It actually is a symplectic integrator. It considers the phase space volume very important if you're really wanting to do certain things. And it is one of the simplest integrators, and it's quite efficient. So you really don't always have to look much further than that. Like I said, if you're looking to solve big problems for long times, you got to start thinking about, I need a big computer. Luckily, we have some big ones. These things are 14 orders of magnitude bigger than the one I grew up with. 14 orders. Can you believe that? Yeah, that's crazy, right? Even from 2012, when we got up and running this new hybrid system. This is a heterogeneous system. It has central processing unit, the traditional computing, and then graphic processing units in it. One of the first hybrid ones. That was the #1 computer in the world in 2012. And that actually is at Oak Ridge National Laboratory. And then China and several other computers has since beat it. It's still #9 in the world. It's unfortunately no longer in existence. We just threw it in a trash can last week. Can you believe that? #9 in the world. This is 20, 30 petaflops. This is petaflops, floating operation, a mathematical operation per second. Peta is 10 to the 15, right? That's a lot. 10 to the 15 of those time steps, right? That's a lot. It's a big deal. And we threw it in a trash can. You know why we threw it in a trash can? Is we had something better. And we're getting something even better. So computing is a fascinating field. The hardware is incredible, right? You're talking about 10 to the 18th mathematical operations in a second, in these systems. And if you don't want double precision, you can do a lot more than that. For example, on Summit, if you're doing double precision, which is kind of nice for most of the things I'm talking about, but it doesn't necessarily mean you always have to do double precision. There's certain cases that you can do single precision or half precision. Say if you're doing a stochastic method, you don't really care that much. It's stochastic, right? So Monte Carlos, machine learning, AI, you don't care. So if you look at what you can do on something like Summit or Titan with half precision, you're talking about already we already been able to do about 2.5 exaflop operations on that thing. So it's incredible. Next up is Frontier, monster machine. Boy, it's hungry for electrons, these things. They like to eat. If you ever have a chance to come down and see this, it's pretty fascinating. The amount of water and the amount of energy to run this system. The water is the cooling. That's how it's cooled. It's just chilled with the water. It's bigger probably than the entire city you're sitting in. Seriously, these things are megawatts systems. Summit is efficient compared to Titan. Frontier is just big, so it's going to be about 40 megawatts. It's $40 million a year for electricity, right? So, you better do something good with this machine, right? It takes up a big old footprint, right? These things are massive. But these exist. They exist now. They're available to anybody to use. That's a big deal. There's many more. There's a couple at Argonne. Argonne's going to get the first exaflop next year. And then Summit's right after that. That's going to be multi-exaflop. Sandia has some. Livermore has some. Berkeley has some. So the ones that are open access to anybody in the room is the ones at Argonne, the ones at Oak Ridge, and the ones that will be Oak Ridge, and the ones at Berkeley. These ones down here are a little less open. Not that you can't get time on them, but they're specifically being applied to national security area. And they are big, and they're as big and as powerful. And maybe we won't always know exactly how big and how powerful they are because there's some of it's classified. But all these ones up here, you can get time on. And if you're interested in learning how to do that, we can chat. If you have time on these, just because you have time on it doesn't mean you can use it to get up to the petaflop or exaflop capacity. You have to do a little bit of computational science work on your codes to make them scale up to that capacity. They will run. It's just they may not achieve the speed limit of that computer. You might as well use the speed limit, right? Luckily, a lot of people have spent a lot of time figuring out how to make algorithms that are common across the gamut of science, including physics, chemistry, biology, but beyond physics, chemistry, and biology. There's a lot of work been done on models and runtime systems to make these weirdo computers work for you. Tools they develop, libraries, these are super important. The math libraries, the solvers, the integrators, the Verlet integrator and various other types of integrators are iterative solvers. Big deal that these work well on computers, otherwise you're not using the computer to the extent you should. This has all been done, right? Ways of using these systems to do really intricate data visualization and analysis and the ecosystems. So this has been going on for a long time, since 2012. So a lot of the work is done, and one doesn't have to always recreate everything. One can just get access and utilize the tools that are already there. And you can start running codes that will scale right off the bat. So it's pretty cool. A lot of effort has been gone into this. So this looks trivial, but it is far from trivial to do these things. Some codes that might be of interest to you, if you're interested in quantum chemistry or quantum mechanics. This also includes a little bit of classical mechanics and molecular dynamics capabilities. NWChem is a code that exists, and there's something called NWChem EX. The EX stands for exascale. So it's part of this project to be able to run at exascale, exaflop capacity right now. It's out there. QMC pack is something we're developing at Oak Ridge. This is a mini-body quantum approach. It's using quantum Monte Carlo, diffusion quantum Monte Carlo. So we're treating all the electrons as electrons. Believe it or not, because it's a stochastic method, you can actually do big systems with that. But you're solving the Schrödinger's equation exactly now. It's a mini-body. We're not doing DFT. This is one of the gold standards. If you want to know the actual potential function or the energy of them, this is the way to do it. It's not ready to solve thousands of atoms yet, but it's up to hundreds of atoms. So available in the open science. You can download it. There's workshops that we have all the time that you can come and learn how to use it and apply it to your problems. Games, another quantum chemistry code. Again, it also has classical mechanics in it and molecular dynamics. They're doing the same thing as NWChem, extending it so that it scales on these big computers, freely available. Something called XALT, which is mainly molecular dynamics simulation, but also has some tight binding calculation capabilities in it. So these are some of the codes. They're on you can Google them up. The information's there. The contexts are there. You can actually download NWChem or games. To get the EX versions, you may have to ask, but these codes allow you to do the molecular dynamics and some of the quantum mechanics I'll talk about in a little bit. So they're there and they exist and they are available to anybody, and they will run on these massive computers that I mentioned. And you guys here at RPI have a fairly substantial, I think you have a petaflop computer here, right? Yeah. I think it's 1 or 2 petaflops. So it would run on your computing system here too. So we got a lot of tools, and we got computers that can make use of those tools and solve things to pretty extreme scales of both size of the system and the time that you're studying the system. So what kind of questions should we be asking? It depends on if you're a physicist or chemist or biologist, but I think these are pertinent questions. One of the things I always wonder is, how do these interactions that the atoms feel actually dictate how a material forms? Does it matter? Of course it matters, otherwise they wouldn't be there. And then, if we can understand that, can we understand how to utilize that and manipulate it to make new types of structures that give you new properties? So simple questions, how's interface drive formation, nucleation? Can we use these tools to answer that? What do you think? Yes? Okay. I think so too. But like I said, if you're using classical mechanics and you have to assume some potential, you got to be careful with what questions you ask. It's going to give you a result. You can say, I want to know how many bonds break, and then I'm going to use a harmonic oscillator. Guess how many bonds will break if you use a harmonic oscillator? 1,000. No, 0. 0 bonds will break. And you'll say, oh, no chemistry happens. Even if I heat it to 2 million degrees, nothing happens. Well, that would be wrong. So you got to be careful. You got to remember what you put in to the model, and it will dictate a little bit what kind of answer you're going to get out. So when you're using classical mechanics, you got to be careful. Even when you use quantum mechanics, you have to be careful. But I'll spend more time on that in a bit. So with that, I'll show you some examples of things we were curious about, and just said, well, can we do that? It takes a big computer to do what I'm going to show you, by the way. These are run on those Titan, which is a 27 petaflop system. And it does scale. The scaling of this is about 18 petaflops is what this is running at. So this is running pretty darn fast, right? 18 petaflops. Solving those simple Newton's equations pretty darn fast. And we need to do that because it takes a long time for this to happen. So this is going to be an example of an interesting phospholipid bilayer system that's got another phospholipid in it that has a serine in it. Serine has an ammonia ion in it. The ammonia ion is this blue stuff. And that's a cation, right? So ammonium is a cation. And this yellow stuff is the phosphate anion. And so you say, wait, cation and anion, they might like each other, right? And so the idea is that if you have a certain percentage of this type of a lipid inside of this lipid bilayer, that it should form some sort of superstructure. And it turns out that it actually forms a pore. And that pore is used to transport material across this lipid bilayer, which is kind of like your cell. So this is a biological application. Millions and millions of atoms in this thing. And the time scale for the poration is close to microseconds, right? Okay, it's not going to take a microsecond. Yeah, it is going to take a microsecond for me to show this. But you'll watch, this is a potential energy function we use. Not hard. You see? It's not going to break any bonds, right? That's a harmonic oscillator, no bond breaking. But it does have charges, and it does to account for those special phospholipids, and it does have van der Waals interactions. Pretty simple function. Yeah?
So I'm curious about I'm familiar with this equation. Some papers we use half, some they don't use half here. And you use it half for the beginning. We said half Kp. And now there's no half. What happened to the half Kp?
Oh, yeah, it's absorbed in the K.
Okay.
Yeah,
okay.
it's just a constant, right? You can do anything you want to with that half.
Yeah.
1/2 K is a function, but it's just absorbed in the K. Yeah.
Okay.
And the same thing with the bins. Yeah. That's a good point. Yeah, you can write them in many ways, but it's the same. But the point is, it's pretty simple functions, and so, but you got to be careful with the question you ask. So I'm not asking whether any bonds are breaking or any bonds made, because this is harmonic. I just want to know whether these things will form a pore over time at a certain temperature. And the red stuff is water. I can't show all the atoms, otherwise you just see water. So the water is the main component in your body. So this is actually a mimic of a functioning cell, and I'm going to watch it over time. And I'm just going to solve those differential equations from Newton's second law. That's all. But there's a lot of them, and I'm actually going to be using one of those big computer systems.
Is this a side view or front?
This is a side view.
Okay.
Yeah, if you do it in 3D, you can't see anything.
Okay.
Yeah.
That makes sense.
Yeah. So as I mentioned, we'll follow it over time. And, well, it's a little blurrier than I thought. You can see immediately these serine molecules or lipids are sort of coalescing and forming some interaction with the phosphate, and then they actually form a pore, and then the water goes through the pore. So it actually does porate. That is a really quick microsecond simulation, but now we have a fully stable pore, and then the water is permeating through it. So you can get ion transport across that into the whatever's down here, which would be the cell. So it matches what we believed would happen. It doesn't always match what we believe would happen. And we can confirm this, because what we can do with experiments is we can deuterate, we can substitute the protons on these molecules that are forming the pore, and then we can scatter neutrons off of it. So neutrons, when they hit a deuterium, they don't even see it, right? So you get this contrast. So you can actually confirm this with neutron scattering. So that's cool. So then you think, well, darn, I can do a lot more now, because I can confirm this poration phenomena experimentally. So this little teeny itty bitty simple potential is good enough to do that. Let me ask some more questions, right? I can do lots of things. So, well, what if I had some other things in this water, say cyanide, or potassium, or sodium? Or what if I heated it up to, say, 40 degrees Celsius? Proteins don't like that a lot, right? Well, they shouldn't like that. We can ask lots of questions now that we have validated our potential and we validated our dynamics. And we can explore many, many conditions that would take a lot of time to do experiment. This simulation took a while, but it doesn't take as long as going in and trying to do the experiment. So it's a powerful, powerful technique, both for physics, biology, chemistry, and many, many other fields. So just the first example. This one is an older simulation, but again, back then, believe it or not, this was done on the most powerful computer. This is a conjugated molecule. It's a polyparaphenylene vinylene system. It's a semiconducting piece of plastic. So it it's not an insulator. It actually has a small band gap. It's about 2 eV. It photoluminesces, and it actually can conduct current, even though it's a piece of plastic. And what we wanted to know, can we make that thing fold up in a precise fashion so that we get all of the molecule connected and the orbitals overlapping, so that we can have a single looking dipole? And what we found is, you can't, if you have it in a good solvent, it just doesn't do anything. It just stays solvated and never folds. But if you put in a solvent that it doesn't like, it is repelled by that solvent, and the thing folds up. And it folds up into a very coherent and nice stack system. So this is conjugated material, so the electrons are sort of delocalized across the entire backbone of this system. And so when this folds up into this little stack, they connect together. And it looks like a single dipole, even though it's a huge molecule. And that's interesting because you can use that as a quantum dot, even though it's a piece of plastic. That's freaky weird, right? And we showed that. So we developed an experimental technique to take that, put it in a bad solvent, as predicted from the calculations, and make a single molecule drop of that stuff. And you can do that. And when you look at the photoluminescence of that drop, the lifetime of that photoluminescence goes on for hours. That's kind of was unheard of back then. So this is a single photon emitting giant molecule that was made single photon emitting by precisely controlling the dynamics so it folded up into this beautifully stacked pi stack system like that. again, computation is able to understand and discover that. It would be difficult to do that just by accident. So lots of really interesting things. Getting that potential energy functions that are used there were very similar to what were used for the proteins we were carrying about chemical reactions in this case. Another example, actually Vincent and I worked on this together. A lot of excitement in low-dimensional materials. There's still a lot of excitement in low-dimensional materials. Dimensions, as I mentioned, make a difference. That's what makes nanotechnology exciting. Long time ago, the interesting pieces was carbon nanotubes and buckyballs, and then along came graphene and got a Nobel Prize. Graphene didn't get a Nobel Prize, but somebody got one basically for graphene. There's always this problem with these low-dimensional carbon materials, starting with the 0D, the buckyballs, or C60, to the 1Ds, and now to the 2Ds, is, we can make enough of them, and we can control the purity of them to the extent that we could really scale it up to be industrially interesting fast enough that people didn't get unexcited. So, carbon nanotubes are still around, and we can do it now after 20 years. C60 is around, we can still do it. Graphene became the more exciting one, because if you can control the width of a graphene ribbon precisely without any defects, you can control the band structure. You can make it a semiconductor. And then you can put it in a transistor. You can do all sorts of things with it. But how to control the width was a real issue. So we thought, well, why don't we just use carbon nanotubes and just unzip them? You cut a carbon nanotube, if either a zigzag or an armchair down the middle, you'll get a ribbon that's exactly the width of the diameter that the nanotube was, right? Just unfold it. Perfectly controlled. But you need to unfold it. Unzip it. Well, you have to break chemical bonds in this case, right? So probably harmonic oscillator is a bad idea. Again, like I said, you got to be careful. If I had used the same functions I was using before for the protein or the polymer, this would never unzip. So the idea here was, lo and behold, you take a multi-wall carbon nanotube and you put it in liquid nitrogen. You can encapsulate the liquid nitrogen in between the walls of the carbon nanotubes. This can be done experimentally really easy. You just got to be careful or your hands will get frozen when you dip it in there. Actually, you don't do that, it turns out. These are really small. And then you just put it in something hot. Okay, well, if you put it in hot, guess what happens to that liquid nitrogen? It turns to gas, it expands, and, well, it can't get out because these things are long, so it's not happy. And it would, in principle, rip that thing apart, right? Just explode it like a submarine deep in the water, and split it right in half. We dubbed this the nano hot dog. Have you ever boiled a hot dog in water and seen it split down the middle? Yeah, it's kind of like this. This is the nano hot dog project. So these are reactive potentials. This is a Rebo potential, it turns out. Very simple potential, but it does allow chemical bonds to be made and broken. The nitrogen is encapsulated inside in a random situation, and then we apply a high temperature, sort of relevant to what the experiments could do. And we watch the different types of nanotubes, an armchair or a zigzag. These are different types of nanotubes as a function of time, and see whether we can split them open. And lo and behold, very quickly we split one open, and out, of course, the nitrogen gases goes away. And if you watch far enough, you can split more open. But the first one that splits is the outer layer, which makes sense. It's the weaker layer, and that's the one you split up. It takes a little longer to split a zigzag nanotube, and there's a reason for that. And you can study the fundamental mechanism and where it starts, where the fault is. And you can actually, believe it or not, relate it to continuum mechanics. There's a fault structure that goes through cylinders, and that's how they fracture. But indeed, we could produce single layer graphene ribbons of a very controlled width using this unusual nano hot dog approach. Experimentally confirmed, and experimentally they've been able to make quite a large amount of this material and validate it. So another example of using these techniques to solve problems and that would be very exciting. Yes?
Are these simulations restrained at all, or are you just
Are these experiments what?
Are the simulations restrained at all, or is the only thing that you're doing?
Yeah, so there's the potential, and the only external thing is temperature. So initially there's gas, nitrogen gas, at very low temperature, so like 0. It's inside the walls, so it's just intercalated between the walls. All right, if you go back, actually, so you got 1, 2, 3, 4, 5 walls, and in between the walls of these carbonyls, a bunch of nitrogen. Okay, so the potential is, there's no external potential. It's only the potential functions. Then you say, I'm going to heat it up. So I put the energy in a random fashion at a high temperature, and then follow the dynamics. So I'm just solving those equations, no restraints. And if you do that, what happens is the pressure builds up to really extreme, very extreme situation, enough to break a chemical bond. Actually, there's topological defects that occur in this thing, and these things take about 5 eV. So it's huge energies. But this is a very local scale, so you're able to do this. And experimentally, they were able to actually do this in the lab and produce these graphene nanorobots. So you notice there's lots of weird things happen here at the edge, and that's, again, potentials are not perfect.
How many walls break?
Huh?
How many of the walls break?
Here, 1. We stopped. The bigger, the lower curvature one is going to break first. This down here, that's going to be rough. There's not a lot of gas that gets in 7 nanometer diameter. You can't get much in there, so you got to have enough gas to expand to break it. I expect the second wall would break after a while.
What's the reason for the zigzag to be harder to break?
So there's this zigzag edge is a very stable edge, turns out. So there's a theory for this. It's called Clare theory, that explains the formation of the defects that split the wall. So the energetics, basics is the energetics. The energetics to basically nucleate the crack requires a lot more energy for the case of the zigzag than the armchair. We have the energy in there, but you have to wait longer for it to localize enough to happen. I didn't, there's more details in the paper if you want to devour that, but there is a whole lot of work that's gone into understanding formation of topological defects. I think Umberto Terrones may even talk a little bit about this in one of these. I'm not sure what he's talking about, but he's the expert in topology. He was also involved in this work, by the way. But yeah, there is a fundamental mechanism for that. Okay, had one more example, looking at what happens when you change substrates, the interfacial interactions. Well, that went really fast. It went faster than I thought it would go. Can you control, if I put down some metal onto a surface and heat it up on different interfaces, can I control the nanostructures that come out of that super hot interfacial interaction? The answer is you can. On the left is one interface. On the right is the more exciting and happy interface. And we can control it to make any structures we want by changing the interface and the interactions of the interface. Again, this is actually a reactive potential. This is an embedded atom model. And we found that there's some funny things you can do with this sort of stuff. You can make super hydrophobic materials by structuring the interfaces so that no water can get on it or no ice. Useful. Turns out, if you have a boat, it's pretty cool. Right, the surface of the boat, if it's super hydrophobic, it can move pretty fast. And understanding the instabilities and how to control those instabilities and what interfaces to use is a big deal to designing new materials that could be non-fouling, so that you could have a water filter that lasts forever, doesn't get contaminated, membranes that you could use forever. So this is a big deal, understanding and being able to study these things. Anyway, so that was a few examples of applications. of the atomistic and Newtonian dynamic systems, both for non-reactive potentials, such as harmonic oscillators, and reactive potentials. Just give you a kind of an idea that, this stuff actually is useful, right? I mean, we can solve it. We can solve it to the extreme cell on big computers, and we can look at things that we never thought we could look at. Next, I'm going to change a little bit. I don't know what time it is because the clock doesn't seem to tell me here. 11. Wow. Well, that went fast. Okay. You can change the atom and say, I don't like the atom, and I would like to have 5 atoms and make that 1 atom. So I can combine units within molecules and call that a different grain. So say I have a carbon to a system graphene, and I would like to say each benzene or each hexagon in a graphene is going to be represented as 1 atom. I can do that. You can do anything you want. That's called coarse graining. So you go from atoms to something bigger to something bigger. So if you have polycrystalline material, you may have the grains of the polycrystalline as independent units. So it's another technique. Again, somebody else will talk about all the details. There's a lot of stuff goes into this. You can't just change it to be that way. You have to have a potential that goes along with this grains that you're using to define the particles, right? So again, you have to have that potential. And John Michael will tell you more about that. But I just want to show you what you can do with that. One of the things we were curious about, because we're energy laboratory, so we like to work on things that have some relevance to energy science. Not that long ago, people got pretty excited about energy conversion. We got a lot of sun, and the amount of energy the sun delivers to Earth is enough to keep us in business forever, right? If we could just take advantage of it. Of course, we don't want to have solar cells that cover the entire Earth. That would not be too good. So we need better ones, right? And we need ones that are flexible and economical. So a lot of people got very excited about this funny polymer that I was telling you about earlier that folded up and is semiconducting as a potential way of doing organic photovoltaics. So most things are silicon-based, the black things that are on roofs. And that works. It's not super efficient, but it works. As you noted with the polymer stuff, thing wiggles around a lot and moves around a lot, so these are not incredibly efficient systems. So we wanted to figure out, can we manipulate it like we did that molecule with the solvent? Can we do stuff to make these polymers better materials for grabbing a hold of photons and ionizing and letting loose electrons? So we wanted to study actual photovoltaic system. So, as I mentioned, that funny polymer that I showed before is a good class of polymer materials to start with. Semiconducting has a reasonably low band gap. It loves to transport holes. And if you add something in that can accept the electrons, you can make an interface. So you have a donor and an acceptor interface. So you actually can have a system that would, in principle, grab a hold of photons, produce an exciton, and then separate the exciton into electrons and holes. Electrons would be on this C60 system, and the holes would be on this polymer system. And then if you have electrodes, you can get electricity. And this does work. Efficiency's horrible. Typically, if you just put this together in a equal distribution of one of these to one of those, you get a efficiency of about 3%. Well, nobody's going to buy a 3% efficient piece of plastic to put on your roof. I'm pretty sure it's economically not useful. So, to be commercially interesting, you need to get about around 15 to 20% efficient. So a long ways to go, right? So how are we going to do that? So we asked the question, what can we do to this system? Can we understand what's going on as a function of time if we mix these things together? So if you look at this big cube here, the white guys are the polymer, and the blue guys are the C60, which is an acceptor. And I'm going to apply a temperature to produce a thin film. And I'm going to ask the question, again, I'm not caring about chemistry here, by the way. What happens to these polymer molecules and these C60 molecules over time? And what type of structure, and can we control that structure? So this was the world record at one time, whatever that means. You know, there's world records in weird things. Actually, about anything you name has a world record. The largest system ever simulated, it was on Titan. It used only 10% of Titan, by the way. So, but it took 5 days of the whole computer to do this simulation. So this is simulating a million atoms system over hundreds of microseconds. So it's a big calculation. If you watch this, you'll see over time the white guys sort of get together and the blue guys get together. And they form these funky domains. And I hollow out the blue guys so you can see in the three-dimensional structure, because it gets kind of hard to see in the 2 dimensions. And after a while, you'll see domains form. And if you measure across these domains, you know, they're on the order of 10 nanometers. And what we know is if you put a photon into a semiconductor material, you form a bound electron in a hole. That's called an exciton. And that thing will recombine and just give you heat or eject a photon. But if you can separate that electron from that hole, you get electricity. And that exciton will travel about 10 nanometers. So you can see there's some bad spots here that are bigger than 10 nanometers. So our question is, well, can we fix that? Can we just change the number of these guys to these guys, or the length of this guy, and optimize this morphology so that the domain size are shorter than the exciton path length, so that the thing will separate into electricity? And the answer is, yeah, you can. I won't show you all the details, but we were able to do that with changing the molecular length, basically, of the polymer. And we were able to compute out of that a scattering function and compare it directly to experiments to confirm that, you know, it's not all nonsense, right? So this was experimentally validated by doing neutron scattering. Again, applying the methods and asking the right questions, you can start doing quite a lot of significant and relevant studies and actually confirm it from experiments. And then you can push it to all sorts of limits. You can ask really crazy questions. Well, I want to add something else in there. I want to have a different loading ratio. You know, the experiments take months to years to do. First, to make the material, it's not trivial, and then to do the scattering experiments takes a long time. The calculations, well, they took 5 days. So, you know, you can do a lot of things. So you can go through and study. The short story is, well, you never get 20%. So, bummer. You know, plastic's not going to replace silicon anytime soon. Another example is looking at bilipid layer dynamics in vesicles. I already showed you the cell membrane, so this is just another example of that. Here we're, again, looking at phase separation. Instead of forming pores, we're looking at just segregation of lipids in a lipid bilayer or a vesicle. A lot of people believe they do form these little domains. These domains are tiny, and the time scale that they form on is short, so it's hard to experimentally observe. Simulations actually show that quite nicely, that you form these beautiful domains, and these domains do penetrate through just like I showed you with the prior case. We were able to do deuteration, as I mentioned, and confirm that from neutron scattering. So that's sort of it for the classical simulations. I'm gonna, yeah, go ahead.
On the last one, it kind of looks like if you would let the simulation run long enough that it would have just formed one big domain, like they kept slowly merging.
Yeah, so you do get weird things happening, as a matter of fact. I don't have that picture. So they'll form bigger domains and they'll bud, and it'll split off and stuff. They do in that experimentally it can be observed, and time scale, yeah, longer. These time scales are really extreme, and that's why you have to do the coarse graining. These are seconds. You know, seconds is a long time on a computer. So indeed, it does do that sort of thing. Any other questions? I still don't know what time it is. 11:19. Yeah, go ahead.
What's the expected parameters that they send you the one? Okay.
What is the
Equation that went,
this equation?
yeah, what's the fix and the equation?
Oh, this is just, yeah, so we have to compute the height fluctuations as a function of time, and you can relate it to this equation. There's a whole bunch of details go in there, but that can be measured experimentally from neutron scattering, in small angle scattering, and that's shown over here. And we can, if we can compute it, we can also predict it, and we can compare directly to neutron scattering. That's all that's for. So we always want to get results out that we can use a correlation function or response function with that data to compare with experiment, because experiment is real and this is all simulation. And sometimes we make mistakes, and if you don't compare, you might believe your mistake, and experimentalists get mad at you when you tell them to go off and make something that doesn't exist. They really get mad. But so we always are computing functions that come out of directly the coordinates and the velocities that can be compared to experimental measurements, spectroscopy or scattering. I think I can stop there, or I can go on to one little bit more. So we can do quantum simulations, and we can solve the time-dependent Schrödinger equation. We don't like to, but we can, right? So we can do that. Or we can cheat and solve Newton's equation, but use the quantum forces that you compute from quantum chemistry or quantum physics. And we can ask questions, well, does it look the same? Is all those jiggles and motions, are they the same? Is there anything different? And of course, there's chemistry is going to be different. But if there's no chemistry occurring, is there any differences? So we said, well, we can do that. Let's see. So this is an example of looking at basically a mimic of an ion microscope. Right? So we have really pretty cool microscopes these days that can resolve atoms at the single atom level, because we focus the electron or the ion beam down to about an angstrom. And we can see angstrom level details and structure. So the question is well, if I do that and I bombard, say, graphene, and I want to image the graphene with an ion beam or electron beam in an electron microscope, does it do anything to the material? Of course it does, right? First of all, it passes through, or it's scattered, or and you can image it, which is transmission electron microscopy. Our question is, well, do we need to use quantum mechanics to study this? Energies, kilo electron volts, it sounds like it's classical. So we didn't know the answer. And we were hoping the answer is no, but not quite. So this is classical. Here comes a bunch of ions, and they're in the beam, and they hit this graphene. The graphene doesn't like it. It does lots of bouncing around. And you see the ions, they get stuck, right? They stick to the surface. They actually, if you do it high enough energy, you'll form graphene. Of course, you have to have chemistry then. We said, well, no, that's not what happens. I don't think so. Yeah, it's a bunch of ions. It's a beam of ions, and we can only do so many. There's only 1,000 ions in this beam because we're going to do quantum also. When a one-to-one comparison, we didn't. So that was classical. So there's no the impact parameter is just zero. I mean, it's direct collision. There's no angle. It's head on. It's 90 degrees. And it would do the same thing with quantum. And, well, there's a big difference. There's no sticking. Excitation is even different. Quite different phenomenon, turns out. There's a little bit of sticking every once in a while, but not compared to the classical. So the classical overestimates everything. The actual interaction to sticking, and you could change the potentials, you can tweak with it, and you can get it to look more like this, but it's very complicated. So quantum does become important even in energy regimes where we were hoping it might not be important. So it begs the question, again, back to the point I made before, is you got to be careful when you apply the techniques and apply them where they can answer the questions without too many. Yes?
When you do quantum simulation, when you visualize it, you kind of get the particles in exact position. You take it as a Gaussian and then put it there.
Yeah, so I'm going to show you how to do that later. Yeah, so I mean, quantum, you don't know really the positions, but this is cheating quantum. So we're integrating the nuclear the positions of the nuclei using Newton's equations, but the forces were computed from quantum. And so it's still Newton's equations, right? Now, we do the time-dependent Schroeder equation for the electrons. So we watch the electron distribution because we're accelerating this and it's colliding. You might be charge transfer and all sorts using the time-dependent Schroeder equation. But the rest is just Newton's equations using electron extraction. Anyway, so I said this, molecular mechanics can be useful for large molecules, but you only get structure, you don't get much more, but it's very important in certain cases. There's this class that I haven't talked about, which is type binding or Huckel theories and all sorts of semi-empirical, which is in between quantum and classical. And then you have your quantum, which is first principle ab initio. And if you solve it correctly, you're getting really the right answers. So we do have to consider all this, and it turns out that, as much as we would like to not believe it, matter behaves like a wave. It behaves like a particle too, darn. Right, so you got to be careful. And back to your question, you got probabilities now and not real positions. The square of the wave function. I was talking to Vincent last night, and he said he put a question on one of your exams or somebody's exams, and maybe not everybody, about a wave function. And it turned out his wave function wasn't normalized, so, got to be careful. Normalize your wave functions, and then square of it is the probability of the position of the particle. So I was actually going to stop here because I think it is basically 11:30, and then drop into some quantum, and then to AI and machine learning techniques, and show you some really cool stuff on how to move atoms exactly where you want to, and feed that back in the next part. Okay. All right, so for the second part, we sort of stopped at, the classical is pretty cool, and we can do a lot with it if we use it for the right questions. There's certain aspects that it doesn't work so well, and I ended it with a movie that showed the difference if you did it classically versus if you did it quantum. And so we decided that, matter, even though it can be a particle and composed of particles, it also behaves like a wave. So we have that duality that we know exists in about all of our materials. So we left off with the wave function, and that leads us to the explicit Schroeder equation, which written out looks something like that. It's pretty scary looking. There's also a time dependence. We can do a lot of stuff to it, and we do a lot of stuff to it, but it's going to be interesting I hope you can hear me with the lawnmower. But basically, it's a partial differential equation, linear one, so it just has a lot of dependencies on the bodies that are composing, which are electrons. So it's very difficult to solve, but that's what we need to do if we want to study things that are exactly modeled and without any approximations. Of course, we can't really solve that thing for very many things explicitly. If you say, I don't want to worry about time, I just do stationary, just don't worry about things moving around, I just want to look at the electronic structure. And I said, well, electrons move really much faster than the nuclei because they don't weigh anything. So we'll just freeze the nuclei, that's called the Bohr-Oppenheimer approximation, and just treat that as a constant. And then you come up with the stationary Schroeder equation. It was a lot better, turns out. And then you try to solve that. You can only solve that for a couple of atoms. Even simple things start looking crappy. This is just a Mathematica solution to a particle electron inside of a double barrier. So, we can't really do it analytically at all for nothing more than a couple of atoms or some really simple ideal situations. So we have to solve it numerically, and even numerically, the number of bodies, which are electrons, are huge, so we're going to have to make more approximations on top of that. So you say, well, classical has approximation, now you took quantum, now you're making approximation, which is better? We're constantly trying to understand that, and so I'll go over a little of that as we go through. So chemists spend a lot of time playing with the wave function, Quantum chemistry deals with the wave functions. They usually use wave function theory. Physics likes to mess with the Hamiltonian, this part over here. Various versions of fixing DFT by adding on long-range interactions. We must throw in some stuff to account for Hubbard interactions or correlations. So people spend a lot of time on both sides. In the end, treating every electron as electron is just too hard. Quantum Monte Carlo can do that, but it is limited, but we're making progress there. We usually say, I don't care that everything's electron, we'll just embed it in the field of electrons, and that's a mean field approach. And density functional theory is sort of along that line. And Vincent's going to tell you a lot about density functional theory, so I'm not going to go any further than just this, that there's these two lanes that people are working on that both make approximations, either the wave function or the Hamiltonian, and it makes solving this beast possible, but you lose something when you make approximations. Again, all these things, the classical and the quantum, there's codes out there that can help you do this. You don't have to write all these codes. And as I mentioned, I already went through these already, so I won't go through them again. You can get started very easily, very quickly, and even on, if you have time, on the computers we were talking earlier, on the biggest computers in the world. And so you can start doing calculations and solving problems really quickly without having to deep dive too far into writing your own codes. There is nothing better than writing your own codes, believe me, because you can't write the code if you don't understand the fundamental mathematics that you're trying to use to solve the problem. So it's a great way to learn. But the great thing also is you don't have to use that when you're done. I recommend doing it, but these codes are solely highly tuned and been developed over 40 years. You can take advantage of those really quickly, and it's good. It's worthwhile doing that. So just give you a couple examples of where we've used these calculations based upon the stationary Schrodinger's equation to answer questions about how to make materials in a specific fashion. First one I'm going to go over is a long time project, but we think it wasn't that long. It was about 5 years. Theoretically, we were interested in carbon nanotubes. As I mentioned, this is some time ago. Graphene is very similar. I'm just going to talk about nanotubes. In particular, we wanted to be able to grow carbon nanotubes to macroscopic lengths. And typically, they terminate after a few hundreds of nanometers, and very seldom you see micrometer type lengths. So we asked the question, well, is there a way that we could promote the growth in a chemical vapor deposition chamber? And I told you a little bit about plasma enhanced chamber, by using other elements than just carbon. Typically, it's a carbon precursor. You put in a vapor phase, and then it deposits on a catalyst, and you grow these tubes. So we said, well, what if we put other elements in there other than carbon, say nitrogen, boron, sulfur? Would they get substituted into the network of the graphitic network for the carbon nanotubes? And if they get substituted in it, what does it do to the structure and the growth? What we want it to do is make them longer, right? So we want something that can act like a surfactant and keep the thing from closing up and terminating. So we said, well, we got to use atoms that fit, right? You put something that's huge, it won't fit in the lattice, and it'll completely break up the network. So the elements next to carbon, boron, sulfur, and nitrogen will fit in the lattice, and their atomic structure is similar to carbon. They're not that much different. So we rationally chose those and said, let's put them in this carbon nanotube and see what happens. And what happens is actually certain elements like to sit in a zero curvature, flat type position, and certain ones like to fit in a positive curvature, Gaussian curvature, where it closes the tube, and certain ones like to sit in a negative curvature, where there's a turn made. So our discovery was that if you put boron in here, it'll mostly want to be inserted into the lattice at a turn. So instead of having a straight tube, you have a tube that grows to a certain point, boron gets inserted, and it changes its direction and keeps growing, changes its direction, keep growing. And in principle, you would get this highly curved carbon nanotube structure that goes on for very long length scales. So, nice idea, right? And all we've done is just said, what's the energetics of putting those atoms in? We calculated that using the electronic structure calculation, solving that stationary Schroeder equation, got these energetics, and found that, yeah, why don't you use boron? So you can use boron as one of the precursors in this chamber with carbon and grow your carbon nanotubes. And lo and behold, gee whiz, that's an actual experimental image of one of the carbon nanotubes. So you get all those elbows with the boron in there, you get those elbows. Without the boron in there, you don't. So it works, right? The synthesis process can be continued on, and in the end, you get a network of entangled tubes that basically looks something like that, ideally, versus when you don't have the boron in, you just get this array of straight tubes. You say, so that's cool. How big is it? Well, it's big. You can hold it in your hands, whereas this is very tiny. This is nanometers, right? So this is macroscopic. So this actually does work. The inclusion of another element, boron in this case, nitrogen won't work. Turns out we proved that from the calculations. It'll just close to. The boron actually promotes this formation of negative curvatures, which is just the direction of the growth, and the continued growth. So you can grow carbon nanotubes that are macroscopic in size. So this is actually this system. What's interesting in this entangled bundle of stuff is mostly it's just a bunch of air, right? It's mostly air. It's about 90% air. So this is kind of an interesting skeletal structure that is mostly air. So it should have funky modulus, right? You should be able to squish that thing. And indeed, you can take that and flatten it out really nicely. Its modulus is really tiny. It's in a single Pascal level. And it'll return because the carbon nanotubes have a really robust mechanical structure. You can flatten it out a million times and it'll still return to its original size. So we dubbed that the great nanosponge because all the space is just like a sponge. It's a pore space. So it should act like a sponge, right? You should be able to put stuff in it and it should get absorbed in these pores. And you could use it, you can squeeze it out because you can apply mechanical pressure. So one of the grad students working on this from Texas, believe it or not, went to the little gas station and got some oil, and then down to the Gulf of Mexico, got some seawater, and poured the oil in the seawater and said, look, that's carbon. Carbon doesn't really like water. It's kind of hydrophobic. But, carbon likes oil because that's what oil is. Couldn't that thing, since it's supposed to act like a sponge, just soak up that oil? And, well, yeah, it can. It can soak it up. You just drop it in there. It won't soak up any water because it's hydrophobic. It's actually super hydrophobic. If you measure the contact angle, it's huge. So it selectively will soak up oleophilic type systems, including oil, in a complicated solution like seawater. And then you can just squeeze it out like a sponge, recapture the entire oil, pure oil, no seawater in it because it's super hydrophobic. Yeah.
I was wondering, when it's filled with air, does it act as a thermal insulator?
Yeah, it would be a great energy. So you can, if you had a piece of it, you could put something hot and touch the other side, you wouldn't feel it. Yeah, it's a great insulator. It would be a great insulator. How practical is it to scale this up to that? Yeah, it's a ways off. I mean, this is where we are. But yeah, absolutely, it would be a great insulator.
It seems very similar to aerogel.
Yeah, it is like an aerogel, except it's carbon. Yeah, it's like a gel, but it's made out of carbon nanotubes. The carbon nanotubes give you some really cool properties, including that they are conducting, have great thermal properties, as mentioned already, whereas the aerogels don't quite have that. But so our original thought is this would be a great electrode, a three-dimensional electrode, and we would have the biggest energy capacity of any battery on the Earth. But creatively, the grad student working on this, he said, hey, this thing with oil contamination in seawater is a problem, and, we don't have the best way of dealing with it. So he showed that this works just fine for that. Yes?
Well, what about in the storage battery?
Yeah, so the storage capacity, well, this is 99% pores. So it depends on the volume of what you have. That's pretty much storage capacity. So in this case, it can hold probably half a liter. But, you get bigger, you hold more, right? Or you put more, you can have millions of these, and just like they do deposited in, they can soak up quite a bit. The other thing I want to mention is that you can squeeze it out, and it requires energy to squeeze it out. So, but that's okay. You're getting the oil out of the water, which is a big deal. You can also just burn it and get.
How do you use those batteries?
Yeah. So, well, you can reuse the oil. Right, so I'm not saying that's a good idea, but it's better than it. But you can reuse the oil, or you can just burn it and then you get heat, and then you use the heat as your energy source. So you can recycle the oil. I'm not sure if the gas station would like that, but we didn't. I don't think we tried to sell back the oil to them. Or you can just burn it. You say, well, what does that do to the carbon nanotube? Nothing. Doesn't hurt the carbon nanotube at all. It's super thermally robust, and you can do this over and 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 over. So it's pretty cool. Just start with a simple question and end up with something pretty neat. And it has other applications too. Just this one's the simplest one to show. Anyway, so that was an example of asking a simple question using quantum mechanics, because we didn't have force fields for this. Somebody asked about this earlier. What about putting other elements in the carbon structures? And this is what we did here. And we decided that we didn't want to work on force fields, so we used quantum, and we finished it really quickly because we didn't have to go through trying to discover what's the right force field. Anyway, so I start from ideas, calculations, to actual synthesis to applications, an example. There's a lot more of these. I'm just showing you some small vignettes. Another thing we were interested, because we were interested in using this as electrode in a battery or a supercapacitor, is how do we understand oxidation reduction? Oxidation reduction is injecting or removing electrons in a material, and that's a hard problem to work with, because the electrons really like to be where they are, and we know they do transfer, and there is charge transfer in batteries. Work based upon oxidation reduction. So we were challenged to figure out how we could study charge transfer in a reasonably quantitative fashion. Certainly we can't do it using classical mechanics, because the electrons are not going to behave correctly with classical trajectories. They are quantum. So solving the time-dependent Schrödinger equation is a good way to do it. Which is that nasty long one that I removed all the time dependence and to do this problem. So now we have to put the time dependence back in. And one of the things we had experimental data on is the collision of two C60s, one that's been ionized to a +2 state, and then one that's neutral. And people a long time ago, probably before you guys were born, were thinking that ionized C60 could be a great space propellant, right? You accelerate it to electro focusing, and you get your propulsion. So there was a lot of work done on ionized C60 in space exploration. We weren't as interested in it, but there's reasons why people have studied this. So on the right, there's a ionized +2 quantum mechanically, and on the left is the neutral. And these things are, I'm starting a movie to show you how the charge is transferred in real time. These are within picoseconds, by the way. It's a charge transfer, a very, very fast process between these two species. This one wants the electrons, this one has them. So already at this distance, which is like a nanometer, you see polarization. There's a charge accumulation over here, this green stuff, the light green stuff. There's a charge depletion over here, there's the blue. And then this guy over here, of course, is already missing two electrons. So as the time progresses, this goes really, really fast. Sorry, because this is quantum calculations, and it's only a picosecond total. You'll see this charge from here transfer over here, and then this thing have electrons all over it. So watch it carefully because it goes really fast. So already done, transferred. Now this guy has electrons, this guy lost an electron, charge transfer happened. And we can do that very, very well with the solution of the time-dependent Schrödinger equation. So how did we do it here? There's a little bit of tricks on this case because even C60 has a lot of electrons, and C60 has twice the number of electrons minus the two that are removed here. So what we had to do is work with a different form of this time-dependent Schrodinger equation. There's many ways of writing the time-dependent Schrodinger equation. The one that typically you will see is one I showed before. But in this case, we want to cast it into a more simple set equation. Basically, it's a Liouville von Neumann equation, which is a hydrodynamic equation. So it removes a lot of the complexity out of it. So all you have to do is solve for the Fock in the density matrix. What's really cool about that is that gives you where all those electrons are, all of them. And so you see the transfer of a charge. And then you propagate the nucleus, the nuclear part, using just Newton's equations. But the force for the Newton's equations is not from an analytical force field, it's from quantum calculations. So you calculate the force with electronic structure, and then you propagate the nuclei with that, and then you propagate the electrons, because we're solving for the electron motion and the transfer, with this equation. And this density and this Fock can be parsed off to different types of processors on these computers. So the Fock can go directly on a CPU, and it does a very good job of calculating those matrix elements. And the density can be put on a GPU is super good for this. And so that case where I had a bunch of particles moving down, each one of them was on a processor, each particle. So it's nearly perfectly parallel. It scales on the order of n to n squared at the slowest because of this trick of casting it into this hydrodynamic equation. So there's ways of doing things without making approximations to the wave function that actually open up new capacity to look at actual quantum dynamics, charge transfer that's really hard to study. Yes?
How long in real time do those simulations?
Oh, there are. Real time. Yeah, so for that system, I think about a day. Yeah, and so that was the first cut, right? I mean, you can, like I said, some of these codes that exist, this doesn't exist in any code yet, by the way. This is something we developed, as I mentioned at the beginning. If you find problems, you have to develop stuff. Without this trick, it would have took years. So that it's not a sacrifice in making approximations to the wave function, though. So that's a good thing. We can speed it up a little bit, and we have by putting, we have more GPUs in our computers, for example, so we can add more stuff on the GPUs. I think instead of a 4x, we're up around 20x now. So the day is not a day now. It's more like 4 hours. I think that's pretty much it, though. And classically, if you could do that classically, it would just take a minute or so. But it's a neat trick, and you can use any type of approach you want to solve the forces for the Newtonian part. I mean, you can use DFT if you want to, or type binding, or full wave function theory, quantum Monte Carlo. It doesn't matter. It's independent of that. So that's what's pretty cool about this technique, and allows you to study nuclear and electron dynamics at the same time. So it's kind of a hybrid. As I was talking earlier, this is an approach that you can also use to solve the nuclear piece of the wave function. Instead of using Born-Oppenheimer and throwing it out, you can actually put it back in and use this technique to solve that. And that becomes meaningful for certain problems. Okay. Any other questions? So this part will go a little faster because I'm actually done with the quantum, because there's a lot of other talks that are going to give you a deeper dive on density function theory, and I don't want to take anything away from that. So far we talked about a bunch of ways of treating materials, from atoms to coarse grain to electrons, and we're using classical or quantum and various types of time-dependent solutions for these things. In general, we always consider things as multi-scale problems. There's certain places where you have to use certain techniques, and we typically do that sequentially versus all at one time. So you have to consider that. I've mainly talked about this area here. But there's much more out here, right? There's micro scale and macro scale where the continuum and mesoscale methods actually apply quite well. What I'd like to let you know and maybe take home is, these techniques, are materials agnostic, and, you can apply it to many problems, and not just materials problems. You can apply this molecular dynamics to all sorts of engineering problems. It's a general technique and can apply to you can play and pool, whatever, or stock market. You can do this. These techniques can be applied to more than just material sciences. Again, like I said, we talked about mostly down here. I want to mention just a couple of things about up here. We do model full castings of engines, so that's a pretty big problem. You won't solve that with quantum mechanics, it turns out, or macrostructure and microstructures. I just want to say a couple words about that level, which is mainly in the continuum level. So a lot of computational engineering is done this way, including design of airplane engines and airplane aeronautics. They do mostly modeling of that in this area. So we know it worked quite well. It's also applicable to some of the structures I mentioned already. Things we've done there is looked at how materials deform at the macro scale. So you're having a really big piece of material and you're applying strain or tensile to it or shear to it. What happens? Processing in the material, recycling the material. Strain-induced transformations, again, tensile or strain or shear. What happens is there grain boundaries, step defects occur. Melting and solidification. One of the first things ever done on a massively parallel computing system was applying these continuum models of finite element technique to simulate car crashes. So this is an interesting story, actually. That's a lot better than crashing the car 1,000 times, because cars are pretty expensive. So all you had to do is sacrifice one car and develop a finite element model. So we had a car specifically that was taken completely apart and then discretized for finite elements and then modeled in a situation where you would have different places where you crashed. And this is accurate enough to allow engineers to address structural weaknesses. And that was work that was done with Volvo, it turns out. But that was done on the Paragon, which was one of the first high-performance computing systems that started the wave of massive parallels. Full car crash simulations. So you can do some pretty neat things. And same thing with batteries. I mean, our lithium-ion batteries, they're not so good when you crash a car with them. They have problems. They catch on fire. They're expensive. The car's expensive. You don't want to be doing that a million times, so we model it, right? We model the whole thing in a continuum process. You can have the battery in the car that's modeled in a continuum model, and the battery can model that way, and you can try to mediate problems that might occur in different scenarios. And then it's just done on the computer, so it's really cost efficient and pretty enabling. So there's a lot at this scale that has been done and largely sits in the area that's of great interest to industry, and has been applied a lot within the aeronautics field as well as automobile field. So I didn't want to leave that out. Some of the other things we looked at is polycrystalline materials. We can treat those each grain as a different object and solve that problem with finite elements, and you can study basically macro scale indentation and strain and pressure squishing materials and understanding those great details. So many things there. This is not one of my areas of expertise, but I did want to mention that it is an area that has a rich set of development and also makes use of the same high performance computing that I mentioned for the other techniques.
Does the scale of a finite element depend on the application?
Yeah. If you underestimate that scale, you might get a bad result, right? I mean, all these things have their caveats and where they will break down. So you have to carefully discretize. So a lot of work has been gone into automatically discretizing the finite elements. There's adaptive meshes that have been developed and work quite well, so you don't have to think about that. And there's codes out there for that. I didn't mention any of them, but they also are codes that are part of this big effort to scale up on the computings. So these things are out there. Main thing I keep saying is, we don't just run the computer to get a bunch of numbers. We really run it to learn something about the material or the process that we didn't know when we started, so we can actually do something useful with it. So one of the great quotes I heard from a Nobel laureate, Walter Kohn, who's the Walter Kohn of the density functional theory, by the way, stood up in one of the meetings at a quantum chemistry meeting where the quantum chemists like to play with the wave function and get numbers that are more accurate than the numbers they got the year before. And so, well, I computed the ionization potential, the energy required to pull an electron out of a molecule at 12 significant difference. Yeah, but I did it to 13. And he goes, hey guys, stop. We don't care about numbers. We care about understanding. And I thought that was a great quote. Compute not for numbers, but to procure understanding. So that's what I've been trying to say here is, you can compute for numbers and you can play around with the wave function until you get a better number, but you don't have to always have a better number. You just need to understand what's going on and get the trends, and that makes a difference to technology and to experimentalists. Nobody needs 12 digits. Experimentally, you'll never get 12 digits, by the way. You get 3. So experimentalists don't care. So all these methods I mentioned are able to provide really useful information, and there's just that one caveat: you got to be careful on where you apply the different methods and which models you use. So with that, I would say the role of theory model simulation is to remove this unusual step here, the experimentalists think. I went in there and measured, wow, it's a miracle. Well, not satisfying, right? We want to figure it out. So that's what I say is a big role here, is we want to understand things, and we can get that understanding by looking into the materials at the atom and electron level and follow the time dependence of these things. So that sort of ends the part on quantum, and I'm going to start going into something slightly different in a second. But I want to just say, these techniques and this approach is being applied to the most recent problems in our fields, in physics and chemistry, the quantum materials, the energy materials, the functional materials such as batteries, interfaces, electronics, and the structural materials, including materials for next generation mechanical systems like cars and automobiles and other automobiles and aeronautics. So there's a rich set of problems out there still, and there's an emerging set of problems out there that's coming along that these techniques will be huge players for developing our understanding. So, as students, you have a great opportunity here to be part of that. So with that, I would like to sort of shift gears. So I talked about first principle techniques. These are the classical mechanics that are based upon a theory, classical mechanics and quantum mechanics, and went up to continuum mechanics. Now I'm going to drop back down and talk about how we can control the materials at the single atom level. So if you could, as Feynman said, you can put all the atoms where you want them, you could do anything you want, right? Basically, that's the idea. So it's not a question of what, it's how, right? How do you move a single atom without moving another atom by it? Or how do you pick up an atom? It's not simple to do, and it's not clear. But if we are going that way, and because we're going that way, we can imagine new types of devices that will push computing and information science to new levels that we can't even hardly fully comprehend at this point. So it's pretty exciting. So as I mentioned at the beginning, if we can move these atoms and particularly put them in positions that allow them to have particular types of behaviors, such as coherence, then we will realize this. Without the material and without realizing it, you can talk about all this stuff all you want. It will not happen without you doing this first, right? So we're pretty excited that it is possible. There is daylight here. And again, as I mentioned, because if we can do that, we will derive the technologies to realization. So I think it's pretty amazing, to be honest. I would have never thought that, Feynman said this before I was actually born, believe it or not, that we would ever actually realize it, but we're getting there. And so I'll show you how we're getting there in the next part. And then the next part's going to dive off a little bit from first principles, because now, we need some experiments because we want to actually move an atom in a real world. So first I would say if you move the atoms, then this was a dream of computational science for many years, is structure properly relationships. And the problem with structure properly relationships is if you don't know the structure to the atomic level, then you'll never be able to predictively use that. You need to know exactly what you have when you're making a correlation from a structure to a property. So, we know that inserting defects in steel increases the strength, but we can't control those defects. But now we believe we can. And so if you can control defects and control atoms and the atomic positions, you can actually specifically design anything you want, and you can form just numerical quantitative structure property relationships that are predictive and are quantitatively accurate. So it's pretty exciting. It's like a holy grail, but it requires you to be able to manipulate or move atoms or their defects precisely. So how can you do that? Of course, we want to understand the materials, the details needed to allow us to do that, and then we want to actually develop the experimental tools to allow you to move atoms specifically or defects or create defects on demand. So we have a pretty big effort in that. This is more of a commercial and then in the content slide, but basically the message is that if you have certain techniques, including microscopy, electron microscopy and scanning probe microscopy, you have a tool that will allow you to move things around. It may be a little stochastic, but if you move it around enough and you collect enough data, you can learn that stochastic process to a level, not quantitative, by the way, qualitative enough that you can control things to the level that allows you to do it. So that's pretty much the idea. And if you can do it, then of course you can do many, many things that I already mentioned. So it's a transition from what I've been talking about before. We make stuff, we characterize it, we do some theory, we do some computation. We usually do that sequence. Now we're going to do it all together, and we're going to add in data that's coming from the computations and from the synthesis and the characterization all together to learn what's going on in these systems automatically, and then use that knowledge while you're doing the experiment to feed back and to allow you to use a microscope to move the atom exactly where you want to. So that's the idea. So this requires a new set of tools. These tools are coming from statistical and mathematical sciences. They're dubbed artificial intelligence, machine learning, many neural networks. You'll hear many different terms. They're all correlative methods, and there's a huge number of them, and there's more now. So if you look in the literature, it can be a little bit overwhelming, and I wouldn't recommend to get overwhelmed. It's no different than the other methods that I went through. There's tools out there. Code-wise, these are much simpler to code up, in my opinion, than quantum by a long ways, and even classical. So very easy to code up. You can write a fairly powerful neural network simulator in 100 lines of you're going to laugh, Fortran. Does anybody know what Fortran is?
I gave a lecture on it last time.
Okay, the most powerful language on the planet, but not so popular anymore. You don't need Fortran at all anymore. Python, you can do it in probably 20 lines. So if I had any recommendation on languages to learn, even though I love Fortran because it seems very logical to me, Python is the way that I think the future is going. So most everything that you'll see in this area, unless you go back to some of the things we did, will be probably Python based. And it's so nice because you can import that into Jupyter notebooks, and I'll talk a little bit about that. So, and we also have our favorite code that we developed that's out there and you can download and use, and it can drop stuff off in Jupyter notebooks. So that our idea is that we want to publish the actual Jupyter notebook code for every figure that, or every interpretation that we make in a paper. So that's where we're looking. Anyway, so just a quick example. Some early work we did. Neutron scattering is a really powerful technique, but it's very expensive because you got to make the neutrons, and that takes about $1.5 billion investment. So you don't have a lot of flux, and so the neutrons are very precious. And you don't want to spend a lot of time doing an experiment, but it takes a lot of time because you never know the alignment of your sample in the beam, if it's correct, and you're scattering and measuring the inelastic part in the right place. So they wanted to be able to automatically, on the fly, figure out how to align the sample in the neutron beam so that they sampled the right part of the electronic band structure. Okay, just how electronic wave function looked like. So there's this inelastic neutron scattering technique that was done at the same time as we ran calculations to calculate what that should look like. So as I mentioned before, we can always calculate things that can be compared to experiment directly. And we found some funky, interesting results in the calculations for a particular alignment that suggested a really huge, humongous road of anharmonicity in these materials. This is barium titanate. It's just a ferroelectric material that had never been observed before. In experiments, we're not seeing it at all. And this is done at the same time. They're measuring and we're simulating it at the exact same time on a high-performance computer. And you said, well, you need to rotate your sample to this orientation because this is the orientation in our model. And they rotated the sample in the actual experiment, and lo and behold, they reproduced the actual calculated results and confirmed this funny, interesting observation from the theoretical side. All done on the same time in the same period. Wasn't a sequential, it was all done at the same time. So that was a big deal. Saying you never would have ever found this, ever. If you did, it would just been, serendipity. So this concurrent modeling with actual experiments can be done and today, and actually is enabling to discover new things that we might not have otherwise found. So the thing we don't want to do is make errors. Okay, that's supposed to be funny. I think it's hilarious. Your quantum computer is broken everywhere at the same time. So we don't want to have that happen. So how do we go about being certain and putting error bars on our ability to do these concurrent calculations and experiments and develop new materials? There's many ways to go about it. Neutron scattering is probably not the best one. It's a little slow. We want something that's a little faster. I always think that, there's nothing more powerful than seeing something in real space. Once you see it, you actually sort of believe that's what's there, right? Seeing is a big part of believing. Seeing a computer simulation doesn't always do it, but seeing an actual electron micrograph makes a difference. You actually see the molecules sitting in a chevron type structure, because that's gold, which has a chevron structure, nicely along those lattice sites. And you can actually do the calculations, see it also. So seeing is a big part of believing. There's a huge amount of work here, and there's various papers, so I won't go over all the details. The best way to see is in real space, I think. Reciprocal space is kind of funky. It's hard to get it. We like to work in Cartesian coordinates in real space. So there's a technique for that. It's called electron microscopy. Electron microscopy has had a revolution. The accelerators that we use to send the electrons through materials has exponentially grown in their ability to focus those accelerated electrons. They can actually focus those electrons down to an angstrom now, and they can accelerate the electrons up to several hundred kilovolts. So they can do some really neat stuff if you throw those electrons through a thin film and have a detector. The other thing that's improved is that they can throw those electrons really nicely and focus them very, very precisely. They can control where they focus them as precisely. We can raster those samples to single angstrom levels on demand. And the detector, They charge a couple devices can detect single electrons these days, and they can detect it at microsecond time scales, real time. So you not only can image something, you can image it over time. You can see things changing in real time. Okay, so that's an interesting. So now we have atomic resolution, and we have actual temporal data in here. So now we got a lot of data, right? So that is a challenge, but an opportunity. So what can you do? You can put a graphene in it. You can image graphene. You say, what's this stuff? Well, this is a Z contrast electron microscope. This is actual real electron microscopes right over here. It's a 100 kilovolt electron microscope that has aberration correction and Z contrast. Z contrast is the Z of the element. So it's proportional to Z. The higher the element number, the atomic number, the brighter. This is actually some silicon contamination on the surface. So they're brighter. So not only can you see where the atoms are, you can actually know what the atoms are also. Now that's pretty cool. So now we're getting to the ballgame, right? Because if we know where the atoms are and we can see exactly where they are, darn, it's easy to make a model of that because that is the model, right? We don't have to make up a model. We have the model from the experiment. So there's a pretty good connection to all these calculation techniques that I mentioned. So very powerful. These are bargain price compared to neutrons. They're about $4 million only. You might want to have one at home. I don't know. Neutrons probably not. That's $1 billion. Yeah, so they are expensive, but the technology in them is impressive and amazing. And what you can do and what you can see is grown exponentially. So you can do more than just see atoms. You can see atom types. And it turns out that, if you focus a beam and move the beam, you can actually move atoms. So this is an example of a strontium titanate crystal lattice here. And there's an amorphous piece over here. The electron beam is focused here and moved. And everywhere the electron beam goes, the lamb is sure to follow, right? So the crystal lattice just grows where the electron beam went. And we can do that with different types of materials on different substrates. And we can do that in real time and control any structure we want by just focusing the electron beam and add a crystalline interface and move the electron beam where we want. So we can grow anything we want. So that's pretty cool, right? So this is real experimental data. It's not calculations. This is coming off of a little experiment. So not only can we see the atoms, but we can actually start transforming them and controlling them with the same instrument that we're using to see. There's nothing more powerful seeing what you're doing, right? And because, like I said, seeing is believing. So we're trying to draw a structure out, and indeed we draw a structure out. All done experimentally. Now you say, how do you do anything with that? Well, you can take a semiconductor and put a dopant in it, and then you can move the dopant anywhere in the material that you want. That's a big deal, right? Instead of drawing little wires, which is kind of cool, we drew wires that spelled, Oak Ridge National Lab, or we could spell RPI, or we could spell University, whatever. It's cute, but that's all it is. But it's enabling if you put dopants in. You can move the dopants. The only problem with the electron microscope is, well, when you have a thick film or a thin film, you're only imaging the columns. You're not imaging inside the material. So we usually use thin film so that you don't have to worry about that problem. And then our idea was, well, let's take some interesting material. Graphene is kind of a favorite, or moldy sulfide, or any of these low dimension materials. Let's use electron beam and let's knock some atoms out. I want to knock a single carbon atom out, and then I want to replace that carbon atom, let's say a phosphorus atom or a silicon atom. Okay, so we have our carbon system. It didn't do what I thought it would do, and we focus the beam, and we knock an atom out here. You can't hardly, it's a little fuzzy, but there is an atom missing here, believe me. This is the actual model, and this is actual experiment. And then we moved this gooey stuff over here, which is actually sputtered on silicon. We moved a single atom next, we sputtered on, and we moved that atom over to that hole that we made. Now it's in the lattice. So basically, I'm doing the engineering at the single atom level. I'm making a material with site-specific single atom dopants. And that model here, actual result here, moving more atoms over here, can be done. Very tedious. Yes? Yeah, next. Good question. Very tedious and very time consuming to do that because, it seems conceptually simple, but they don't just go where you want them to go. They kind of move around a lot. But if you're a patient, you can get one to move to some place that you particularly want because the potential is going to be minimum in a hole. But it's not like pool. You don't just shine it and it goes over there. It just goes because that landscape is rather crazy. But a dedicated graduate student postdoc that lives in the lab can move 2 atoms in 2 positions, 3 atoms, and 4 atoms. So yeah, the question is, well, that's not scalable, right? I mean, even though that is impressive, is very impressive. These are single atoms, and this is real results. You're going to have to do something about feedback and automation. Yeah, so good question. So indeed, that's what we want. So we have these coils that allows us to position a sample in the X and Y direction, not in the Z direction. We can tilt the samples and go in the Z direction. So we have control. Typically, the control is automated and it just rasters back and forth. So you expose the entire material to the electron beam and you image it. But we don't want that. We want to hold it in one place and move it to a certain place. And if you can understand how that atom moves on that surface, you can use that understanding to feed back and move the position of the sample so that you don't have to spend all your life in the laboratory. That's where the machine learning techniques come into play. Just doing the experiment, providing the information to the machine learning techniques, they find the correlation to the beam position, the beam energy, and where that atom goes. And they can do that very, very efficiently. And then you can have this feedback system that allows you to position and move any atom in that lattice to any place that you want. So that's the concept, is to do that. So that's not going to be the quantum mechanics or the classical mechanics technique. That's going to be this class of artificial intelligence tools that's taking the data directly. And we don't want to necessarily wait to do it after the experiment's over. We want to do it during the experiment. So it has to be very, very fast. It needs to get that data, interpret it, feed it back, tell it where to go, and move it there, and then keep on doing that. So it has to be a very fast learning system. So that's where we have to connect these pieces. So a lot of people have been working on these tools. Google has been all over it, right? And Microsoft, Google, these large corporations. You have self-driving cars. I'm not going to ride in those for anytime soon, but they do exist, right? That's pretty impressive. And today, most of the applications of AI has been in this realm of self-driving cars, pattern recognition, beat me at chess or GoPro or whatever. That wouldn't be hard, but they beat the best person in the world, so it's pretty impressive. Those exist. And then, over here, we're doing things, single atom. We base upon our long time experience in physics and chemistry and knowledge. All we need to do is hook the pieces together. This powerful set of tools that allow us to do things automatically with our traditional tools that we do in the lab every day. And then we have a way of doing what I said we need to do in terms of feedback and automation. We can automatically do it with a car. Why can't we do it with a microscope, right? Seems simpler than a car. If you wreck the microscope, you don't die or anything, so it's a good thing. Although it's $4 million and the car is less. So that's go. So manual approach can be done. It's tedious and takes a lot of time, and I guess somebody would go crazy after a while doing that every day. And then, typically what you do is, well, I don't want to do that. I'll just do some selective analysis. You miss a lot of opportunities in the data. Selective analysis or particular suite of applications to analyze the data is always prone to error. And there's a lot of information that we're missing, let alone this feedback process. So that's the concept that we want to work on, and that's something that we've been developing at Oak Ridge National Laboratory. We call it the atomic forge because we're basically forging a material by removing atoms and placing atoms where we want to, just like we would in forging of steel. So it's kind of a nice name. And we've been able to do a lot of things in this process and fully automate the microscope to allow it to have this feedback so that you can actually say on the computer screen. So you go in the computer screen, you have a little appy that you say, I want to take this atom out and I'll replace it with another atom. And the system will go and bombard that atom with electron beam, remove it, and go grab another atom and put it in there. That's pretty cool, right? That actually can be done and can be done today. So I think it's pretty exciting and pretty enabling. It has required a combination of fairly large amount of experiments and some novel tools coming out of statistical and mathematical sciences in terms of AI and machine learning to do this. So it's a little bit different than some of the other techniques. Here's just another example of what we can do. We can move things around. We can watch the images. But in the end, it's nice that we move atoms over here and put them where we want. But we also want to understand the physics that was underlying that. So we do want to extract physics out of this. So these machine learning techniques, as I mentioned, are not based upon any theoretical foundation. They're just statistical techniques. They don't have physics in them. But it doesn't mean you can't go from watching the image to understanding the physics that's causing this motion and the particular defects and dopant motions that you see in the actual real experiment. And you can do that with machine learning through combining different types of machine learning techniques. And like I said, there's a whole bunch of them out there, and there's a bunch of terms, and I won't go through all of those. But for imaging, the best technique is a convolutional network. It does exceptionally well. So typically, we will use a convolutional neural network to go from an image that's collected off of an electron microscope to the data that is analyzed by the machine learning directly. That convolutional neural network, which just looks something like that, a bunch of nodes and different convolution layers, is able to do that with quantitative precision, 99% accuracy. Not too bad. So it's pretty robust. And then you can extract out some of the physics using clustering methods. I won't go through that in detail, but I'm glad to talk about it during questions. And Markov systems, you can actually start extracting out fundamental physics like, well, what's the diffusion coefficient for that atom? What's the diffusion coefficient for this atom? If I change the electron beam energy, how does the diffusion coefficient? If I change the temperature? So you start learning the same things you learn from the ab initio approaches, but now you're doing it with a different class of modeling techniques that's basically running explicitly off of data, a data-driven technique. So it is a new realm of computational material sciences, and it's starting to grow very quickly, and I think it's a very viable area for folks to look into, not only in terms of fundamental physics and chemistry and material sciences or biology, but also in engineering and all types of aspects, including self-driving cars, which Google is already doing. So this is an example of what we can do. Again, our favorite layer of material. This one is tungsten disulfide, it turns out, that has been doped with molybdenum. So the tungsten is going to be brighter and the molybdenum is less bright. And we can train that neural network to detect any defect in the system that is caused by just shining the electron beam on it. Because like I mentioned, if you focus the electron beam too long, you'll knock atoms out and then atoms will move. And that's a defect. And you can train this neural network by just using a set point. A perfect crystalline lattice is what it should look like, and any breaking of that symmetry will be a defect. So that's what the neural network basically learns, is symmetry breaking in a lattice. Now, if it wasn't a lattice system, you'd have to have a different way of training this neural network. But for this case, we were able to just teach the neural network that there are certain types of defects that will occur. It automatically finds them. It always detects every defect that occurs. And then you can categorize these defects in different types. So this is molybdenum-doped tungsten disulfide, which is hexagonal lattice system. And you find systems where there's a substitution of the tungsten with the molybdenum, which is here, which the molybdenum is not as bright as the tungsten, so it looks dimmer. You have an add atom, which is just a molybdenum or a tungsten sitting on top, which is this stuff here, this white stuff. You also have cases where you have another type of situation that looks different than the first one, which is just a molybdenum substitution. And then you have ones where you actually just knock the atom out and there's nothing there, a vacancy. So the atoms that are easiest to knock out are the sulfur, the chalcogenide ones. They're easier to knock out than the metal. Much easier, much lower energy to knock out. So you're actually not, these are sulfur vacancies. And there's a couple classes of these sulfur vacancies. So there's only basically 5 types of defects occurring in this image that was found by the neural networks. And that seemed to correlate quite well with what we can see from the images and do with the tedious by hand analysis. So it was able to identify these, classify them, cluster them correctly on the fly. And over here on the right, you're seeing these different defects, how they move over time. Now, I challenge you to tell me the diffusion coefficient of any one of those boxes. Be hard, right? It's moving pretty fast, and this is running over, like an hour, right? This is an hour time scale. But the neural network, because it's following these and it knows where every one of these are, can cluster them into specific types, and you can show that you can actually cluster that. You can plot it. You can see these are the defects in the different types, and it's just hard to see anything in it. It's kind of pseudo pretty. Initially, there's no defects, and all of a sudden, there's all sorts of defects, and some of them kind of don't do anything. They don't move in space at all. They just stay kind of constant, right? This is time on this axis. And these are seconds, by the way, and these are nanometers. So this is over a large length scale. And some of them are they're moving all over the place. So we can cluster each type. So like I mentioned, the sulfur vacancy is one of the biggest ones. And you can cluster those into 2 different types of trajectories. And then you can plot out the trajectory over time and get the diffusion coefficient. And that works quite well. And if you do a Monte Carlo model of this, you get the same diffusion coefficient. And I didn't do any modeling here. I just used the machine learning to classify those defects and understand how they diffuse during time, because I'm taking images during time. So it's automatically classifying, clustering, and extracting physics out on the fly just based upon data. Pretty neat, right? I think it's neat. Anyway, so what we're doing now is we're building these tools and putting these into databases, defect databases. There's a company called Citron that allows you to put open source databases, and we're providing these data that we're getting from the experiments to Citron so that anybody can use it. We're now including not just electron microscopy, but you could ask the same questions. Well, what would a scanning probe STM or AFM look like? It's a little cheaper than $4 million to do STM AFM look like. So we can we don't have to do experiments, because on this, to be honest, we can do calculations. So what we did on the FM or in the STM cases, we did density function theory calculations, all those defects, and projected out what they should look like, and let the neural network learn from the calculations instead of experiments. You don't have to use experiments. And now we populate the database with defects, both for scanning transmissional electron microscopes and scanning tunneling microscopes. And so that one can access those and utilize that information for these materials. You can also use these techniques to guide you to where you may be missing some data. This is just more of a workflow slide, which basically sometimes you have enough data to understand certain aspects of a material, but you're missing something and you don't know what it is. That's a hard problem to figure out where you need to do the experiment or where you need to do the calculation. So the machine learning can help guide you to do calculations or do a specific experiment to understand a particular property directly without having to randomly search over an infinite space. So with that, I just say that we do develop the codes here and offer these codes directly to anybody. You guys can go download it if you have a computer. You can download it now and want to. It's all in Python, as I mentioned. It allows you to do the image processing and the data analytics fairly efficiently. It's all easy to install. It can run on anything, your laptop, I guess probably your cell phone. Maybe if you work hard enough on a cell phone, it would run. I never tried the cell phone. I expect it could. It works equally well on these high-performance computing. So we're making it completely community-based and open to anybody to use these things. Like I mentioned, you can port it directly to shareable workflows such as Jupyter Notebooks. With that, I'll take one more example. I told you this wouldn't take as long as the first part, but if I didn't take any deep dives. This is an example of making some weirdo device. It's a fidget spinner, but it's a nano fidget spinner. So I have to go back so you can see it. So everybody's familiar with fidget spinner. It looks something like that. Except this fidget spinner we directly made out of polymers on purpose. So we CAD what we want to make, and then we write it at the nanoscale. And then we spin it. You know, that's what fidget spinners are for, right? So this is just an example of it is the world's smallest fidget spinner. It's classified as that. And it actually spins. There's 4 of them spinning. So we use ultrasound to provide the energy to spin because they're too small to actually spin. And this thing is shown in one of our traveling science trailers. You can go in and look through an optical microscope, and you can actually see it. So if you ever see the Oak Ridge Science trailer, the physical sciences one, you can go in and actually play with one of these fidget spinners. Isn't that not practical for anything, but it's kind of cool, right? Yeah. So, well, this one is in micron size, actually. Yeah, you can do this same thing with the other stuff. You can get it down to nanometer size, but you can't see an optical microscope then, so you can't put it in the science tray. You need an electron microscope. And
So what's being seen?
sonic ultrasound. Yeah. If you sneeze, you lose them, right? You can't. They're not very big. Oh, you can make anything you want. It's just 3D printing at the nanoscale. That's what it is. So everybody's heard of the additive manufacturing, 3D printing. We do it at the nanoscale, and we can do it at an atomically precise scale. And when you do that, you start enabling new properties as well as kind of cool stuff. Nothing practical about that, but these sort of fun things get more references than the other stuff by far. So again, I just like to say that even the data-driven approaches such as machine learning and artificial intelligence, which are extremely powerful but not based on a theory, doesn't matter which method you're using. The role is not to think everything's just a miracle, but to actually dig out what's really happening. And once you do that, you can start controlling things and building devices with precision that deliver the performance that you really want them to do. Thing I will end with, even though I don't think I've spent a whole hour yet, no, it's almost 3, goes faster than you think, is challenge. So we work with industry, even though we do the fidget spinner is maybe industry level, but are moving atoms and making precise defects that give you catalytic processes. You can see how the catalytic process would be interesting to the beer industry. That makes sense. But we work with a lot of industries. One of the industries that we work with is Procter & Gamble. I think probably everybody may have used some of that this morning when you got up, soap or dishwater soap or shower or your clothes. They make all these detergents and surfactants. They make a lot of them. And it's one of our biggest commodities in this country as well as the world. And they have a lot of problems. many industries don't have research, fundamental research efforts anymore. So they come to universities and national labs to get that talent, right? And they invest at the universities directly and at the labs to solve problems that, well, they can't solve themselves. So computational science is highly sought at in terms of this. And the drug companies still have efforts because drug design is a huge economical effort and also a payoff. So they do still do it. But most of the chemical companies and even some of the bigger engineering companies, GM and these things, kind of outsource a lot of their fundamental science and to universities and national labs. So Procter & Gamble came to us and said, look, we make a lot of detergents, such as for dishwaters or dishes, for shampoos for your hair, and various other applications. And what we find is, the shampoo is weird. It is a colloidal suspension, and it actually has polymers in it. Shampoo has plastics in it. Did you know that? Yeah, it does. It also has a bunch of other stuff, perfumes and foamers and deposition agents. It's a sea of stuff. It's a really complex mixture. I mean, it would be really complicated to fully understand all what's going on. But what happens is that this simply has a lifetime. Did you know it has a lifetime? There's actual expiration date on it. You know what happens if you go past the expiration date? It's kind of like milk. It phase segregates. It separates. You get like a sour milk on top and cream. Yeah, so they have this problem with shelf lifetime, and shelf lifetime depends on how that bottle shampoo is delivered to where it's sitting. So, if it goes by train, it has a different lifetime than if it goes by bus or it goes by plane. And they said, well, this is a real problem for them because they can't figure out what to put on the expiration date on the bottle. They're just guessing, right? Of course, I think educated guess, but they said, well, can you understand what's going on? Yeah, whoa. So how would you do that, right? I mean, well, what's in it? Oh, we can't tell you that because that's a secret. Okay, so now that's a problem, right? Well, it's a bunch of surfactants. It's got some polymers, and it's got some silicone in it, and it's got some perfumes. It's got some coloring dyes in it. Now, wow, can we remove the dye? No. People won't buy it if it's not colored. It turns out, oh wow. So it has to maintain that composition because that's the composition they can sell. So you just have to understand what causes this time dependence of the composition to decompose and phase segregate. So they challenged us with that and said, can you do the modeling? Can you just figure out what's going on? So that's my challenge. How would you do it? So the tools we talked about are capable of looking at phase segregation. Remember when I showed you the lipids, the one picture of the lipids phase segregating and clustering? That's phase segregation, right? So we could do that, right? We could set up a really large simulation and say, okay, we don't know exactly every element that's in that solution, that mixture. But we know that there's these particular components, and we'll just change their interaction types and see what happens, and go back and say, look, if you have this sort of silicon polymer surfactant interaction, it'll do this. If you change it to have this interaction, it'll do that. What is the range of interactions you might have? You got to work with them because I can't tell you there's that composition because that's a secret. It's a trade secret. And that actually worked quite well. We're able to understand that and not only understand the dynamics and the phase segregation that occurs over time, but what happens when you shake it differently, right? Shear it. And so that gets to be less comforting because you're applying the mechanical strain in very large force. Because when you wash your hair, believe it or not, the force that you apply to the poor little soap molecules is enormous, huge shears. So the shear rate is excruciating. In the simulation, we just have trouble capturing that on the right time scales and the right shear strengths. So we weren't as confident in that. So we said, well, can you give us, you don't have to give us, we just go to the supermarket and buy it, right? But we want, well, they give it to you. Bonus, free shampoo. We'll put it in a shear shell. And that sounds like a commercial, a shear shell. Okay. And do neutron scattering of it during the shear and see if it correlates to what we're calculating. And so, like I've showed many times, we always calculate stuff so we can compare directly to real experiments, and then we can be confident with our models. They didn't have to tell us composition anymore, right? Because we're just comparing the results from their actual sample to simulations that has no information about the composition. So we can go back and forth and get the agreement, and then we can start believing the results from the computations and use the computations to answer questions about how to improve that stability of those mixtures. And so they said, well, that's cool. We want this tool. So fine, it's open source, so it's not a problem. He said, well, now we want to put it on hair. Oh. And we want to understand how it coats hair, how the soap is deposited on the hair, and how it removes the dirt and the oil from the hair. That sounds like another interesting problem, right? So now composition is complicated. Now we're wanting to see actual hair in there too. It's starting to get big, right? Hair's big. So we said, well, we can look at substrate deposition. I mean, I showed you a lot of examples where there was a substrate and something was on it. So we know we can do the molecular simulations of that. Experimentally, we used a new technique called helium ion microscope, which is just like electron microscopes use helium ions to image and study these things in real time. So we had a comparison, and that worked out. And they said, wait, well, we have one more problem for you. We've got to put this stuff in a container. It's this plastic bottle, and the bottle has to have an interesting shape or nobody will buy it. And it has to be transparent because nobody wants something they can't see what's inside it for some reason. I don't know if you feel that way, but apparently their marketing people says it has to be transparent, has to be kind of a cool shape. And they said the problem with transparent and cool shapes is when we move them down our little conveyor belt. So what they do, they start out with a preform that looks something like this, of some plastic goo, and that thing gets inside of a blow injector. So it heats it up and just blows air in and pops out a bottle. And that bottle falls on this conveyor belt that's just a regular conveyor belt. And it moves down that conveyor belt. And it gets to a point where a robot arm grabs it and sits it up, and it fills it with their solution. And then it closes it, and it goes off to the truck and sends it to the store. And they have a minimal acceptance rate, so how many bottles they have to fill per hour, or they won't be able to make money. Very important for them. And so they were trying to replace their entire manufacturer line with this new technique. The old technique basically was a giant centrifuge that they spun around, and the bottles would fall down into a hole, and then it would stand straight up, and then they would fill it. This new technique used actual lasers to detect where the bottle was, feedback with automation to tell the robot arm to pick up that bottle and put it over. And so it's very important that the bottles didn't cluster together, because the robot gets confused when the bottles are clustered together, can't pick up one. So they were going to replace a multi-million-dollar facility, like several $100 million facility, with a new technique, but they couldn't figure out how to keep those bottles from sticking together and jamming. So jamming processes are very common, and this is part of chaos theory. And they said, well, we don't understand why these things keep sticking together and jamming. And we can't replace the manufacturing processes unless we don't have that happening. So can you help us stop that from happening? And wow, I started with this crazy problem and solutions in the hair, and now the bottle. The bottle is the hardest problem, right? Turns out that because the conveyor belt is made out of material, and the bottle's made out of plastics, it's dielectric, and it's moving, it pulls a charge. So this thing has electrostatic charge in it. And the electrostatic charge causes it to attract its neighbor that has a different charge, and they stick together because there's this electrostatic charge on the surface. So all we have to do is get rid of the electrostatic charge. So we did experiments to show that, actually, this electrostatic charge is the major driver for this thing to be sticking together. We used the atomic force microscopy to pull out the exact forces. We were able to put that into actual models and model it. And said, the only way you can get rid of the charge is you're going to have a flood gun to neutralize it, or put in something that doesn't let the charge accumulate on the surface. So we worked out ideas on what to add to this plastic preform before you made a preform that could compensate and neutralize any electrostatic charge and wouldn't change the actual plastic material, so it still could be transparent and still be blow molded. So another example, a very long one, of solving or help solving. We didn't solve, we just helped. And they actually started and launched and built this actual new production line in West Virginia last year. So pretty cool. Again, modeling simulation combined with experiment, very powerful. You use a lot of different ways to decompose a problem to the right length and time scales and answer questions that are meaningful and validated with some experimental data, and you can go a long ways. So with that, I'm going to just end. Thank you. I don't know how much time's left. About 15 minutes, looks like. So I can answer any questions or